Hello, YouTube. Mic 2 on YouTube. You're live on YouTube now. Sing. Mic 1, live on YouTube.
Podium mic, live.
Mic 3 online. Do I have mic 3? Don't worry. Put the camera. Okay, in the room, mic 2. Mic 1 in the room.
Podium mic.
And mic 3.
Yes, because Mark is still sick. So.
Yeah. Wait, sorry, you're live on
sorry. No, he'll do it.
Mic 2.
Mic 1.
Podium.
Mic 3.
Fine. I'm sorry, my hand is wet because I just washed it. I like the title.
On attend 2-3 minutes. On commence à 5 pour laisser assez. Le temps que les bus en retard arrivent. Yeah. Okay. No, just checking that this is on. Morning, everyone. We're gonna get started. So please take your seats, and if you're having breakfast, just quietly. Welcome back. Happy to see all of you here. We've waited a little bit, expecting that some of you would be late because of the snow. A few reminders with respect to what we said yesterday. So first, if you have questions, there's the Zulip chat. The QR code will be up. You can ask around. Most of you are already signed up. We'll share the slides of the talks on Zulip and on the website. We'll actually put them on the website, and then it will be shared on Zulip. And if you have questions during the talk, please do stand up and go to the mics so that the questions can be recorded for YouTube and for future users who want to listen to this. So without further ado, we're going to start today with the second day on GFlowNet, and Kolya is going to be the chair of this second day on the theory of GFlowNets. So Kolya is a postdoc here at Mila with Joshua, and he focuses on probabilistic inference algorithms for structured latent variable, and is interested in applications in vision and language. Kolya, the floor is yours.
Thank you. And I will proceed straight to introducing our first speaker, who is Joshua Benjou. He may not need an introduction, but I will remind you that Joshua is a professor at Université de Montréal, a scientific director of Mila, and among many other honors, a fellow of the Royal Society and a recipient of the Turing Award for his contributions to deep learning. And lately, he is also focusing on making sure that artificial intelligence has a positive impact on the future of humanity. And he will tell us now about why GFlowNets are interesting.
Thank you, Kolya. Thank you, Victor. So, it's working. Yes. That was the first paper, NeurIPS 21. And it happened after not so much time, I forgot exactly, maybe just a few months, that we stumbled on some of the early exciting properties of these that I'm going to say a few words about, but of course you'll hear a lot more later today. I'm sure Emmanuel will do a good intro. As far as I'm concerned, maybe the most important property of GFlowNets is that they are stochastic policies that generate objects, let's call them X, with some probability distribution. And when the training objective, and there are many choices, is minimized, they will be sampling these objects with probability proportional to a reward function R of X. So whereas generative models are typically trained to imitate a given distribution specified by a data set, GFlowNets are generative models that will learn to sample when provided with an normalized distribution function or a reward function or an energy function. It's all the same. So they solve a different problem than the typical generative models. And of course, we use the word reward because a lot of the ideas, and that's to Emmanuel's credit, and really came from analogies with existing reinforcement learning methods. So this was a paper led by Emmanuel, and Moksh and Maxime played an important role, especially in the experiments. And this was kind of co-led by Doina and myself. All right, so why just a few months after the paper did I write in my blog, I have rarely been as enthusiastic about a new research direction. So I'm going to try to focus on this and maybe, depending on time, go a little bit deeper on some of these things. So the first angle came because we were working on trying to design new molecules that would have certain characteristics, certain properties that we could put in the reward function. So we wanted to find molecules that had high value of this reward function. And initially we played with just standard reinforcement learning methods, and Maxime had initiated that almost a year before. But we found that standard reinforcement learning, and this is not like a new thing we discovered, it was well known, tends to lack in the diversity of solutions that it finds. In fact, the optimal reward maximizing policy is going to generate a single object that has the maximum reward. In scientific discovery, for example, for drug discovery, which was the thing we were thinking about, you really want to have a diversity of solutions. And there's a number of good reasons why you want that. The reward function we're using is not the true one that we care about. It's a proxy, it's an approximation, maybe it's been trained from data. And so it could be wrong. And so we don't want to put all our eggs in the same basket. So diversity of the solutions was really the initial motivation. And there were some existing methods in reinforcement learning based on adding entropy regularization to reinforcement learning methods, but they had some issues that I'll mention that made them not quite what we wanted for the problem of generating molecules. Now, as we developed the ideas that led to the first version of the GFlowNet, something really important dawned on me, that we were doing something quite different in nature in the way that we train these neural nets than the typical neural nets. So the typical neural nets trained by maximum likelihood, you have an objective and you just agree to descend on it. But the sort of problem we're trying to solve with GFlowNets has an intractable objective because it involves, for example, the normalization constant of the reward function that is intractable. We can't compute gradients through that intractable quantity that has an exponential number of terms. But what's going on in GFlowNets, in a way that's, we got the inspiration from this from temporal difference methods, is that instead of directly optimizing for the thing we want, like the log likelihood or something, we reformulate the problem into a set of constraints such that when these constraints are satisfied, we have what we want. Now, there's a catch. The number of constraints is exponentially large. We can't possibly visit all of them. But this is like a new kind of objective function that, if minimized in expectation over choices of these constraints, has the right properties. So the right property, as I said, is that we are going to be sampling these objects proportionally to the reward function, which means from the target distribution we're looking for. So that's very interesting. And the Bellman equation and reinforcement learning has actually a similar structure. We take the local Bellman constraint, and then we write like a squared error loss. That is what people will use in TD lambda, for example. But we brought that to a different kind of problem of sampling proportionally to a distribution. And in addition to sampling, actually, the methods we developed were also marginalizing, meaning computing these normalization constant, and then we found other sort of marginalization. So marginalization means summing some quantity where the sum is usually intractable, so we can't just do the sum. We have to use some other trick. So the trick is we train some neural net or some scalar in the case of the partition function that, if we minimize the objective, computes the right sums. So these intractable sampling and intractable marginalization abilities of GFlowNets when they minimize their objective is something that got me really, really excited, because for about 2 decades, I had realized that essentially all the good things we want to do in machine learning can be solved if we can do marginalization and sampling in cases that are intractable. So where it's not easy to do because we are dealing with 2 high-dimensional spaces. And this is exactly the job that Monte Carlo Markov chain methods are in principle solving. But I'll come back to, they have some problems. They actually would solve the problem with exponential computation. And when you have finite amount of computation, they end up finding solutions that don't have enough diversity, which was the thing we started with. And I'll try to explain why we're getting more diversity with GFlowNets than with MCMC. The GFlowNets, then it took us a while to figure out, actually happened to be connected to other machine learning methods for dealing with intractable inference. And these are the variational methods. And we wrote a paper that came out at ICLR this year that explains this and how they're related to these variational methods. In fact, you can think of GFlowNets as a variational method where we don't use the Kale divergence as to define the objective, but something else that has really nice properties, again, that help us with the diversity question. So the typical Kullback-Leibler-based variational methods, which are the ones that have been studied in the literature, like MCMC methods, suffer in typically finding one or a few modes of the distribution, but getting stuck there. And MCMC methods also get stuck in the same way. So yeah, there was another reason why I thought this was very important. I had been working with my group and collaborators for many years on bridging the gap to human intelligence with this notion that current neural nets do well with system 1 abilities like intuition, but not so well in system 2 abilities, which have to do with reasoning under uncertainty. We do a better job. And when I, started playing with ChatGPT, the first thing I tried was like, make it solve some of simple reasoning tasks. And it failed. So what we need to solve system 2 is, according to me, these reasoning under uncertainty capabilities. And that's what the probabilistic inference abilities of GFlowNets or their descendants, which have yet to be invented, can do. So yeah, that's in summary why I was so excited. Let me now go quickly through some elements, maybe to clarify the abstract things I've been saying, and you'll see a lot more depth in the coming talks, I assume. So think of a neural net that will sequentially generate a compositional object. And what we started with as compositional objects are graphs. So you can generate a graph by generating one edge at a time, picking a new edge to add to an existing graph that has been partially constructed. So the neural net decides at each step some action that makes us move towards the completion of the task of sampling the object we care about. And in the language of reinforcement learning, we're just learning this policy that decides what to do at each step. And then at some point chooses a special action that says, we're done. We have the object we want to sample. And then we're going to get a reward. Okay. So these neural nets take at each step the currently partially constructed object, like a graph, like in the figure, say here, that has these 3 nodes and 2 edges. And it chooses the next action, like adding a new edge that connects a new node 4 to an existing node 2. Okay, so we're going to learn these policies, which we denote PF for forward policy, which move the state in the reinforcement learning sense, which is a partial construction, to the next state until we end up in a special terminal state that says, oh, we're done, we have the object we want. And one way to analyze this that really helps develop the intuition, so why it's hard and what are we trying to actually do, is this figure that Emmanuel managed to do some trickery, where you see the little blue things are like drops of water that are flowing in this directed acyclic graph. So what is this directed acyclic graph? Well, it shows the different states corresponding to partial constructions. It shows that we're going to start with an initial state as 0, for example, like an empty graph. And it shows that at each state, we have a choice of different actions that bring you to a new state. And there are also special states, which mean we're done. When we choose a special action here, like there's a T for terminal action. And of course, here it's a cartoon graph. The real DAGs that we care about are exponentially large. First of all, the number of states is exponentially large. And the number of trajectories in, to construct these things is also exponentially large. And the thing that makes things complicated is that it's a DAG, it's not a tree, which means that there are many ways to land in the same state. And that is the thing that previous work in reinforcement learning couldn't deal with. So in the original paper, we had a first constraint that had the property that when satisfied, the policy defined with the output of the neural net would sample as we wanted, so proportionally to the reward function. And the constraint had to do with, looking at this DAG and saying for each state, look at all the water coming in and all the water coming out, and they have to be the same. It's kind of conservation of flow. And then we can turn that constraint into a loss by taking like the log on both sides and taking the difference and squaring and minimizing, making sure that these losses are minimized everywhere, at least according to some training distribution, gives us what we want, that we're going to sample the objects with the right probability, which is the reward function normalized. And of course, we can't compute that normalization constant, and it's intractable to even sample. Okay. And one of the key ingredients here is that we can choose the distribution of trajectories in this graph that we're going to be using to train the GFlowNet. And that makes GFlowNet very special in terms of reinforcement learning, in the sense that, we call them offline learning, because the configurations or the trajectories that we train on don't have to be the same or coming from the same distribution as what the current policy has as a distribution. So at any point, the neural net defines a distribution over trajectories, because at each step you choose to go, left, right, this next state or that next state. But that distribution is problematic, because if it only likes some particular kind of trajectories and there are others that is missing, it kind of never gets to see those good trajectories that it's missing. And so it never reduces the loss at those points that it doesn't visit. And that's the problem with the existing variational methods. But with GFlowNets, we're able to train on any distribution of trajectories, so long as it has not, it puts mass everywhere. And so if we have some clues about where the missing modes could be, we can use that. In practice, one of the tricks we use is we take the current policy and we consider a tempered version that has like a higher temperature, so it explores more. And so that seems to work, but one of the open problems is, can we do better than that? So why is it that the MCMC methods aren't that great? They're great for a lot of problems. Like a large part of physics and chemistry relies on these methods, but they have an issue, as I said, in terms of diversity. They tend to find just a few modes that are easy to find. So the way that MCMC methods work is by taking a current candidate solution and then making stochastic moves in the neighborhood of that solution, where most of the time you would try to make it better, but sometimes you allow to make it slightly worse in terms of the reward function. And so the problem with that is, because in order to move from one mode, one region where the reward is high, to another mode, you have to go through a number of steps in which the MCMC procedure, doesn't want to go. It has a low probability of picking these steps moving away from the currently good solutions. And if you need a long sequence of small steps to go from one mode to another, it becomes exponentially unlikely that you will find a way from one mode to the other. And so they tend to get stuck with the modes that are easy to find by just random perturbations and then going down, going up in the reward function or going down in energy. So how could you possibly do better, right? It looks like so that's part of like what really got me excited very quickly about GFlowNets, which is, I thought exactly 10 years ago, after playing with all kinds of MCMC methods for training machine learning systems, that it was impossible, that we couldn't find those modes that were hard to find and away from the ones we already had. But that's using traditional MCMC methods. that don't take advantage of the knowledge that is being acquired as you move around in that space trying different things. But machine learning methods have this ability, not always, but when they're successful, to generalize. Meaning, for example, in the toy scenario here, that if the learner, so now we're learning, right? We're taking advantage of the information we're gathering as we try things. If we've tried a bunch of things and we found these 3 regions where the reward is high, it may give us clues about other places far from those we've seen that may also have a high reward. Like, the missing grid corner here looks like a good place to look. And indeed, I think recently Alex did experiments which I thought wouldn't work, but actually similar to this, and the GFlowNet discovers these modes. So that's why I got excited that machine learning generalization abilities could come to the rescue to solve or to make progress on these apparently intractable problems in probabilistic inference. Another advantage, which is more practical, is that once we train our GFlowNet, once we trained our neural net, it can generate samples very quickly, whereas MCMC methods need to go through, very long chain of small steps, which potentially could take exponential time before they visit the things we want. And this ability to generalize across modes when sampling carries to the problem of marginalization, which is summing over all the modes. So actually, I have a little bit of math, if I can. So I'm going to focus on the problem of marginalization. First, I'm going to show you that neural nets already do things like this, but not quite what we want here. So if you train a neural net with squared error laws, so the neural net here estimates is S of X, right? It's trying to estimate that sum of the expected reward. In the context X, we're trying to sum over values of Y. And we're given a sampler P of Y given X. Nice. So if we define a loss like the squared loss here for our neural net as hat, and we minimize this in expectation over the sampler P of Y given X, it's very, very easy to show that you recover the right thing, expected value of Y given X. It's like machine learning 101. Regression. Okay, problem is we don't know that sampler P of Y given X. So we just have the integrand, the summand, the thing, like reward of XY, and we don't know how to sample it. And so the idea here with GFlowNet style solution is gonna say, aha, we don't know how to sample and we don't know how to marginalize to compute that sum. But let's solve both problems at once. So we're gonna learn 2 things. We're gonna learn a sampler, which here I wrote like pi hat of Y given X, and we're gonna learn a marginalizer S hat. So S hat is approximating the sum that we want at the top, and pi hat is approximating the normalized reward distribution, which is the sampler. Okay, and then you can do like trivial algebra where you say, okay, so the sampler pi y given X should be equal to the reward normalized, where S is the sum, remember? And we can take that equation and take S, which is in the denominator, put it on the left-hand side. So we get the third equation. And that's a constraint. That's the constraints I've been talking about. So now take the log on both sides, put the square, take the difference. So log of the product minus log of R. And it's trivial to show that when we get that loss to 0 over all XY pairs, this constraint is satisfied. And it's also trivial to show that once the constraint is satisfied for every XY pair, you get the property that you want. The sampler is the right one and the marginalizer is the right one. So that's really what we're exploiting with GFlowNets. And I think I will stop here. Thank you. You have an exam after.
Questions?
Yep.
If there are no questions, let's thank Joshua again for this introduction. And now I'd like to introduce Emmanuel Benjo, who will give us the introduction, the first technical introduction to GFlowNet. Emmanuel is ML scientist at Valence, formerly known as Recursion, where he does research on the union of GFlowNets and drug discovery.
Thanks, Goya. So for the record, recursion absorb valence, not the other way around. So valence is parts of recursion. No worries. So yeah, you've heard from Joshua, and I will be repeating some of the stuff, but hopefully with a different perspective. And also, petition is great to learn. So I'll start again with, there you go. I think by now you've heard what a GFlowNet is. I love this slide because sometimes people come to me and they're like, so GFlowNet, that's what kind of architecture is that? I guess we did not choose the name optimally. It's not a neural net architecture, but you've heard that already. So GFlowNet's generative framework where initially we designed it to sample combinatorial objects. It's still used a lot for that, but we can now do continuous things, and I think you're going to hear about that later today. And what are the typical combinatorial objects? Molecules, that's where we got started with GFlowNets, but also proteins, language, Bayesian networks, all sorts of things. Yeah, I guess I'll tell you more about how we came to that. Again, as Joshua mentioned, during the pandemic, we kind of threw some reinforcement learning at COVID, hoping to find cool things. We did not find an antiviral, but we did find new algorithms, and that was very fun. And the context setting was basically, we were doing search, we were doing reinforcement learning. We had some reward function, some way to quantify how good a particular molecule was. But of course, that reward function was extremely noisy. In particular, those familiar with the context, we're using docking, just some kind of low resolution physical simulation of how, let's say, a small molecule and a protein interact and how much energy is between them. That's of course very noisy because it's only an approximation of physics. And that meant that you could kind of easily fool that reward function, and lots of candidates looked good. But even though lots of candidates look good, it's still a kind of needle in a haystack problem. You just have lots of needle, and your haystack is 10 to the big number. And finding really different kinds of molecules that all maybe were interesting according to that reward was pretty hard. So hopefully you find that set of solutions and you send them to your wet lab and you get more data to kind of bootstrap from. But the big question is, what do you want to send? And the traditional way that people have done this in all sorts of contexts is apply some ML, generate a batch of candidates, and then kind of manually or heuristically pick the best, including some notions of diversity. And that could be like for molecules based on scaffolds, but for all sorts of things, you may want to cover your state space intelligently. But this is all handcrafting. We would like not to have to do that. So, the motivation is what's a good technique that finds something diverse by construction? And, why is diversity important? I think Joshua has given some pretty convincing arguments. I have more. In organic chemistry, biology, physics in general, but all sorts of domains. As I mentioned, the proxies, the reward functions that we have are very, very imprecise. They're sometimes models of models of models. And so they can only get you so far, right? You're seeing on the right here this nice animation of docking at a more kind of refined level here. And that's really cute, and it's really helpful for someone to understand what's going on when they're trying to understand a molecule, but it's really an approximation. The real world is more complicated, right? This protein might be living in a cell and being jiggled around by many other processes, right? So again, this nice four-mode picture that I think you're going to see a lot. We want to cast a really wide net. If only one of these modes is actually correct, we'd really like to have one candidate in each of these modes, not just for, let's say, in the same mode, if we're only allowed 4 picks. In reality, of course, the state space, the reward space is way more complex. You don't have these nice, easily separable modes, probably have much worse. So diversity is important there, kind of by construction. Another reason I think it's important that I'm actually working on with other people is we know that neural networks can generalize pretty well, but that heavily depends on what data they're trained on. And as we've mentioned, the more kind of modes you see, the more combinations of different features you see, you would think that a model would want to go to this different mode, right? That's kind of a nice property of generalization and a nice property of getting an energy-based model to go everywhere. And the neat feature of GFlowNets is that they have this kind of by construction, right? As they learn about their reward and their state space, they induce their own training distribution, because typically we train them on policy or on policy adjacent with some exploration stuff. And so as GFlowNets learn, they kind of build their own really nice training distribution, which I believe kind of takes fully advantage of the generalization capabilities of neural networks. So that's another argument for diversity. You've heard about RL and MCMC yesterday. Can totally use them to solve these kinds of problems. So for example, for drug discovery, for molecule design, again, we have an MDP, right? We have actions and rewards, but exploration in RL is a very complex topic, and it's really hard. And in practice, when we apply RL methods, we do tend to see problems with diversity, as has been mentioned. And same with MCMC, mode mixing, a hard problem, right? In kind of expectation in the limit, MCMC gives you the right solution, but you don't want to have to wait forever. And we can also use the usual generative models. The kind of downside of this class of models, usually, although there are, of course, extensions, but the main ones that you've heard a lot about, like diffusion models, are typically based really on having a kind of data set of positive samples, right? So I show you 1 million images of cats and get really good at generating cats. But for something like molecules, because we have this scalar reward instead of this, yes, this is a cat or yes, this is a dog, there's more information in that scalar or in those scalars if you're doing multi-objective optimization. And we don't want to waste that information. It's really useful information. So I'm going to do some reward proportional model. And of course, we want to avoid doing MCMC. So you've seen this before, I think, yesterday. You see it again during your practical sessions. Kind of intro combinatorial objects is, of course, something like smiley faces, where you pick, am I gonna choose the eyebrow like this or the smile like this? And the really important thing to notice is that there are many ways to build one given face, right? So for this evil smiling face, there's a number of trajectories that lead to it, and it's very important to account for that. Again, we are in a setting where we assume that we have some kind of reward or energy function. And what we're going to do is use that reward to associate a flow with each state. In particular, for the terminal states, we're going to think of them as sinks. You can absorb all this flow. And the initial state here on the left, you can think of it as the unique source in your network. Right? And so we end up with this flow network. The very important part to kind of get the right properties that we want, that you want all your flow to be conserved everywhere. So for example, here, right, you get 3 units of flow kind of flowing into that state. And here, for example, this intermediate state only has 1 unit. And you'll see that if I pause at the right moment, you'll see that it's kind of split in 2 because that state has 2 parents. And then we combine again here, and then we combine again here. So you can do that for all your states, and you end up with a flow network that you can use to sample fixes. So how do we do that? We define this policy that we'll write PF, which if you're in some state S, to decide which state to pick next, stochastically, you assign a probability to each transition that is proportional to the edge flow, right? So here for a particular edge, we take the flow on that edge and divide by all the other flows outgoing from that node. And the really neat thing is, as you mentioned, this gives us a nice generative model. Oops. The ratio here that we're choosing induces a really nice distribution where if all the flows are preserved, of course, the probability of sampling some particular state is going to be proportional to the flow that's going into it. And then that's, of course, extremely useful. Maybe I'll stop there again to see if there are questions. No questions, so I'm assuming everyone here understands. Great. Yeah, so, done this for smiley faces. We can do that for molecules. Here's a really cartoon environment, but in reality, we'd have a lot more things. And so if we have a lot more things, we can't actually, instantiate this flow network in memory. It wouldn't fit. So we have to use function approximation, and we're going to do just that. Typically, we use neural networks, but you can use anything. For example, for molecules, we can use graph neural networks. And what we're going to do, or rather the first thing that we did in the first GFlowNet paper was to estimate edge flows, right? So you have some edge, and typically the parameterization we would use is kind of give a description of that state as an input to the function. And that function would output a number of scalars, 1 per potential next state. You might see in the GFlowNet papers, they're often referred to as actions. That is, again, some kind of historical accident, I want to say, because we kind of inherited all the RL terminology while thinking about these things. It's pretty common in reinforcement learning to think of, I'm at a state, I can take some actions. Here are the actions I like, go to next state. But you can think of them here, for example, as one action being add this new fragment to this existing molecule. And so, seen it already, but hopefully seeing it again will help. One way to encode this desire to train this function approximator is to think of the constraints that we want, right? So given a state, we want all the flow that's coming into it to be equal to all the flow that's coming out of it. And then for terminal states in particular, we are assuming that they're sync states, and so we want all the flow that goes into them to be equal to the reward. Again, we're assuming here the reward is given. The nice thing is that, once again, if those conditions are satisfied and we're sampling trajectories from this policy that we've defined, then it's guaranteed that we sample from the right distribution. So, of course, the first reflex is to turn these equations into a mean squared error. And this is kind of exactly what GT0 is doing. Actually, for a large enough state space, that would be a terrible idea. So I'm going to go back a bit here. You'll notice that at the root, right, the initial state actually contains a lot of flow. In fact, you might have noticed in the slides, I don't know if it's been very explicitly mentioned, but what you actually recover is that the flow of the initial state is actually equal to the partition function, which is the sum of all rewards in your network. And the bigger your network is, the bigger your state space is, the bigger this quantity is going to be, right? So if you have 10 to the 60 objects that you can, possible objects that you're constructing, and for a lot of objects, this reward is something non-zero, the value of Z might be extremely large. So if you're taking mean squared errors here, you're going to have a bad time because your neural network will have much larger losses for the early states because they have a lot more flow, and will kind of maybe be really good in some sense predicting their flow, but really bad at predicting the flow of terminal objects because the losses there will be extremely small. So what we do instead, and I think what you'll notice we do for basically all the GFlowNet objectives, is we operate on a log scale. And the utility of doing that is that now the value of a mean squared error on a log scale will be kind of invariant to the scale of the flow that you're modeling, right? So close to the leaves, close to the terminal states, the difference in log between two predictions that are wrong will kind of have as significant magnitude than the loss on the early states. And that, it turns out, is pretty important to make the whole thing work. So this first objective, we call it flow matching, and I think, yes, there you go. And there's some interesting things about this objective. First of all, if you do it on the log scale, it's not that bad. If you make your neural network output logits, then these two operations are log sum x operations, which can be numerically stable. And in addition, you can also use an epsilon value that you would add to both terms to kind of stabilize learning here. Actually, your epsilon term here can do more than just stabilize things. It can actually, as I was mentioning, give a preference to the model to ignore some of the very low flow objects, right? So earlier I was saying, if you have, let's say, lots of very small flows and you're doing a linear mean squared error, the mean squared error will be tiny. Whereas if you do it on a log scale, it'll be the same everywhere. If you add an epsilon after bringing these terms into a linear scale, if the flows are really small, the rewards are really small in the case of outflows, then the epsilon will kind of bring back again its mean squared error to be really small. So in flow matching, that can actually be used to help the model ignore lower reward states. Second point is, so for those familiar with temporal difference methods, you might be wondering, why are we, using the same network in the target, and why is it not detached? it might be weird to to think of it from an RL perspective, because we're so used to kind of thinking of maybe fitted key iteration and stuff like that. But here we're doing something pretty different. First of all, maybe your MDP is deterministic, right? So if you think about a double sampling issue that Q-learning has, you wouldn't have it here because, well, you always have the same sample when taking a transition. And then I think maybe it's not quite correct to think about it in terms of RL and temporal difference, because really we're just satisfying constraints. And these kind of locally must make sense and also globally make sense. On top of that, you're using a neural network which will generalize, right? So it makes sense for kind of both sides of the equation to inform each other in terms of loss. So once you have these things, usually, I think most people will train a GFlowNet online on policy. You'll hear later today, and I think tomorrow, about more ways of training GFlowNets that will do some exploration or some offline training on samples. But the basic training loop is very online RL, right? So you start at the initial state, you start the smiley face example with an empty face, and you take actions to build an object and sample a trajectory using the policy that you've constructed. And then once the agent says, okay, I'm done, stop, receive the reward. And then we collect a bunch of these trajectories and apply the flow matching objective along that trajectory. Because I was mentioning, this is like the basic thing to do. There are lots of tricks here, of course, but basically, yeah, one thing I didn't mention, of course, but I think Yoshua mentioned, is that these objectives are off-policy objectives, right? As long as you have a cover of all the state space, you don't need to be following your policy to learn the correct values. And that means that if you have a data set of trajectories or data set of samples, that can be used to train your model. There's lots of ways, and you'll hear about this more, but the basic way is, you start with some high reward objects and you kind of bias the mini batch of your model to see more of these objects. Of course, doing that will induce some trade-offs. So if you show lots of high reward objects to your model, it might think, oh, there's, problem solved. I already kind of found all the interesting things, and it might not learn to explore properly. So of course, another kind of off policy you can do is exploration methods. There's lots of them. And the kind of basic one that we've been doing, but of course we should be doing better, is this epsilon online trick that I think people doing Q-learning and variants are very familiar with, where you basically follow your policy, but with some small epsilon chance, take a random action. This works, but of course we can do better. So, of course, one downside of the flow matching objective that I just talked about is that it's very local. What do we mean by that? It only considers, a single state in some sense and learns around it. So the state won't be very informed by the trajectory that it's in or the reward that was part of the trajectory it was in. This has some advantages, but then at the same time, it makes learning very slow because the temporal credit assignment has to kind of propagate slowly from the reward at the end of the terminal states back to the initial states. Another downside of flow matching is that it's very expensive. The main reason is because of these sums. So as I mentioned earlier, the typical parameterization of a GFlowNet that uses these edge flow predictions is you train a neural network, and this neural network's input is actually the initial, well, not the initial state, but the first state on this edge, right? And let's say that this state has 100 children, so 100 actions. You'll simply output 100 numbers, 100 logits for that particular state. Sorry, yeah. So for the outflow, that's not a problem, right? You have one state, and then you just output 100 kind of digits. For the incoming flow, though, it's a bit more complicated, right? So you'll notice here S is the input, is on the left-hand side, but here S is kind of one of the outputs. And to take the sum here, you actually have to enumerate all the parents of that state S. Not only do you have to enumerate them, if there's 100 parents, you have to do 100 forward passes of your model to get the edge flow for that particular edge. And 100 is not that bad, but in some cases, if you're doing molecular design on the atom level, or you're doing natural language in some funky way, you can end up with an enormous number of parents, and that's just not scalable. And so, yes, that's expensive. As I mentioned, this is related to bootstrapping in reinforcement learning. Bootstrapping has a lot of issues. There can be drift, right? Because you're not just bias that induces drift, because you're kind of trusting the prediction of what happens in the next states that your model is doing, and that can lead to a lot of bias and make your model take a very long time to learn. So today you'll hear about much better variants that are more efficient, but also less biased and more stable. You'll also hear about better parameterizations. So once again, the parameterization here is on the edge flow, but all you need is some way of getting flows. And you can get that indirectly by multiplying things, but no spoilers, you'll hear about that. And finally, of course, as with any method, lots of tricks can help. Some from reinforcement learning, of course, replay buffers in various ways can help. Target networks that are some kind of moving average or kind of old version of your model can help stabilize sampling or just learning. You'll also hear about various forms of intrinsic rewards that may help with learning stability or exploration. You can also grab tricks from MCMC. There's a very recent paper that I'm on where kind of combine GFlowNets and MCMC in a very simple way, where you kind of start a trajectory with GFlowNet, land somewhere, and because GFlowNet is diverse, you kind of get that diversity for free. But then you can use MCMC to do some kind of local refinement of your reward. And we know that's going to work because MCMC is very good at exploring locally within a mode. You'll hear a lot about temperature as well. It's very common that if you kind of take some random reward function and some random setting, the scale of it will be a bit wrong, right? So for example, if in your state space you have 1 million objects, and almost all of them have like 0.5 reward and 10 have 1 reward, the total mass of the 0.5 reward objects is still 500,000, right? And so the probability of sampling those will be really high. A simple trick, of course, to kind of lower the probability of those 0.5 reward objects, increase the reward of the 1 reward objects, is to use the temperature. So one thing that we've been doing that you'll see again in papers is just raise the reward to some exponent beta. Usually that beta is some hyperparameter, but it can also be part of the input. So you can learn temperature conditional models. but it's also something that can be scheduled during training. The trick that you'll hear about, I won't go too much into it, but you can use data sets and maximum likelihood to do interesting things. Yeah, so thank you for listening. And I think I'll take questions, and then Kolia will tell you more about these new objectives that we have.
Nice talk, Emmanuel. You motivated like GFlowNets and then compared it with RL at the beginning, right? And one of the challenges you mentioned was like exploration in RL. It wasn't clear to me how GFlowNets could explore more state space and then gather more data. Like, could you?
Yeah, maybe let me go back to, well, you know, one of the caveats of RL is that, at least let's say you're doing soft key learning, which is like nice Maxent method, you should get for free some proportionality, but that proportionality is a bit pathological. If there are n paths to this state, then the probability of sampling it yeah, the probability of sampling it will be something like number of paths times the reward, proportional to that. You know, for smiley faces, it's not that bad. You only have like 6 paths to here, but for a molecule that has, you know, 50 atoms, you have an unfathomable number of paths, and this bias will lead these methods to do weird things. Another advantage, if you compare to just like even more traditional VDRL, is that some greedy RL method might find one mode and be kind of happy with it because, well, it's find a pretty optimal policy. And maybe we can get it to explore, but like it takes a while before the policy learns, oh, I can also go there. In contrast, GFlowNet wants to do that by construction. There's no built-in exploration mechanism, and it wants to spread the probability mass everywhere, and that kind of naturally makes it explore. I don't know if that contrasts them well.
Yeah. Also, like, do you assume like you know like what molecule fits with what other molecule? Because if you don't know, then you might have to explore all combinations to decide like which ones are fit well, which ones don't, and then it kind of like boils down to the same exploration problem, right?
Well, you have to assume that your reward contains some information, and that some of this information can be captured by a neural network, right? So either the reward itself, right? So a typical scenario is you send 100 molecules to the lab and you get some reading out of them. And then you train a neural network, random forest or whatever, on those 100 data points. And that gives you some predictions. And then you can feed in new molecules to that neural network, get new results, and you use that as your reward function. And what you do is bootstrap from that. So you train a generative model, you get maybe 10 new molecules, send them to the wet lab, and then you kind of grow your data set. But you have to trust that there's some information in there, so that this model of reward that you're training captures something. And then that model has to also have structure so that the GFlowNet that you're training to match that reward function can also have some structure. Otherwise, of course, it's kind of hopeless.
Yeah. Also, I was thinking of distributional RL. Like, I mean, like, what's special about sampling according to rewards? Question A. And 2, can we do this with distributional RL and get much more with that as compared to GFlowNets? Like, any thoughts on that?
Let me start with distributional RL. Distributional RL is about a parameterization of the value function. It's kind of fundamentally the same algorithm. You're learning to, you're learning the value function of the optimal policy. It's just that in distributional RL, instead of learning the expectation, you learn some distributional form of the value function, of the random variable that the expectation is modeling. But you're still learning the same function. In GFlowNet, you're learning an entire object entirely, different object entirely, which is about, this energy-based style model. Can you
So you could
expand on your
potentially
second? Sorry.
you could potentially sample actions once you have the distribution or value function or the value of the state. You can potentially sample actions using any of the metrics, right? Not just expected value. Maybe you would want to sample like quartiles based actions or things like that, which kind of gives you like diverse policies essentially, right?
I'm not sure that's correct, but I'm not a distributional RL expert. One thing I do know is distributional RL will give you something like risk averse policies, because you can look at the variance, let's say, of the value prediction of different actions and pick the one that's high reward and low variance. But I don't know about using that for diversity, because the best diversity you'd get is diversity of rewards. So you could do the inverse of risk averse. You can do risk seeking, right? You pick the action that has the most variance. But then that just means you might sample low reward actions. Here you can, still sample high reward objects. It's just because of the smoothness, you have this diversity by default. I don't know.
Thanks, Emmanuel.
Hi, I have a very naive question. Okay, so I specialize in physics and I'm not an expert in this field, but in physics, when we look at flows, in nature, we also can have backflows. So I'm wondering, why are all your transfer of information in one specific direction?
Yeah, I guess here we're just using flow as a very convenient analogy.
Yeah.
Not too familiar with what a backflow might be. I think so here we kind of design these flow networks to be acyclic DAGs. And that's very convenient, because then we don't have to think about edge cases.
Mm-hmm.
You could actually have cycles in here.
Yeah, that's what I'm thinking. Yeah.
It would induce some problems, but we think we can fix those problems without too much difficulty.
For me, it just seems that you would add another dimension, like you would add more exploration. So it might be logic.
Yeah, I'm curious to know what a backflow is, but maybe come see me at the break. Thanks.
Thanks, Emmanuel, for the great talk. So I just wanted to go back to the slide that we were describing how we can train GFlowNet offline. So you mentioned that maybe we can initiate the samples that have high rewards, but what if we don't have access to that, high reward samples?
Yeah, so something that works fairly well is a replay buffer where you only keep your top N samples. Right, and then that kind of counts as leveraging a data set. Is just your data set is dynamic. And that works pretty well. But then there is this trade-off sometimes of if you're too greedy, too high reward with the data that you show your model, then.
Okay. Yeah, but so what if, okay, so I understand that, replay buffer actually keeps the, you can have some sort of a priority in your replay buffer and keep the samples at high rewards. But what if we actually, there's a scenario that we cannot assign rewards to those trajectories. And maybe you can do some sort of clustering and just, figure out what samples have more values to the task that you are trying to solve.
Are you saying if you don't even have a reward function, what can you do?
Yeah.
Okay, so I mean, we have some results where if you have a data set, you can do the energy-based thing basically and learn the energy function as you're training your sampler. That's totally fair game. You were talking about clusters. Maybe you could, if you don't have a data set, but you have some notion of distance between samples, you could use that distance information, clustering information to build an energy function or reward function. I think that would also be fair game. as long as it's consistent with the problem you're solving,
Yeah.
should be fine.
Okay, thank you.
So yes, I had a similar question related to the one before. Like, why are you? What are the reasons of using flow instead of weights, for example? No, it's like to apply the condition that the input it has to equal the output of flow, or is there any other reason, like for using flow instead of weights? You know?
I mean, the flow is just a metaphor.
Yeah. No?
There's not the physical interpretation here. It's really just a convenient way to think
More
about the
visual,
problem.
maybe, or to explain the concept. No. Yeah, I was like curious about it, because usually we see like weights in the neural networks.
Well, so
but you are defining like the ratio flow that could be also like the same concept, no?
So like this is this is a flow network, but not a neural network, right?
Yeah.
We never actually see this graph anywhere. Like we don't instantiate it in the program. It's only implicit in the fact that we have an agent that can like build faces, right?
Okay.
So what the neural network sees, let's say, is like a face, and it makes predictions about that face. In particular here, for the empty face, it makes 6 predictions, which kind of tell it which action to pick, which next face to go to.
Yeah, more rewarding, no? Okay. Okay. I think it.
A quick question regarding the training. You said this was done online. I wonder how this does this mean that for each, for example, given molecule, you're going to have like one online learning pass? Or is there a way to like leverage the fact that different molecule problems might have similarities, like aside from the reward function?
Not sure I get your question. So
like basically, are we just like, when you learn online like this, is it like one sort of online learning task for each different molecule you're trying to learn?
Yeah, so one thing we assume is that the reward function is somewhat cheap to compute. And if it's not cheap, like you have to send something to a wet lab, then you can train a proxy for it. There are ways around that, but they all kind of, in my opinion, equivalent to training a proxy for it. And then, yeah, so you're just seeing a molecule, training on it, and then you kind of throw away that data because you want to learn about different molecules.
Okay, so basically, like it's more the compute time than the data. You really want to go like one example at a time or like one problem at a time, but you're going to just like, I don't know, use as many compute cycles as possible, and hopefully you're going to like converge towards the like right distribution.
Yeah, that's correct.
Okay, thanks.
Thank you for the talk, Emmanuel. So I had a question concerning the structure of the GFlowNet. Like, I was wondering, what is the advantage of having many trajectories that lead to the same terminal state instead of having a tree for your GFlowNet? Because like one helps to share information, but it also makes the problem more complex because you have to learn more things.
Yeah, I think that's actually an interesting research question. So there's 2 things. One is for something like a molecule or a smiley face, we could canonicalize the order in which you build it, right? So we could always choose the left eyebrow first, then choose the right eyebrow first, then the left eyebrow, then the mouth. Then we would have a tree. Sometimes that's actually really hard to do. For very symmetric objects, like molecules, for example, that you define atom by atom, there's not a good way to canonically build them such that you'll end up with an MDP that's always a tree. Let's say you're building this little triangle here. Well, actually, I don't know if that's a good example, but I think, sorry, I'm trying to think of an example on the spot, but like, if you're building this ring, here, like a neat canonical form would be you always have to start with the oxygen and then the other carbon atoms. But like for more complex molecules, that's not always possible. And you end up with different versions of the same thing, depending on which of these carbon atoms you start with. And in the general case, you can't enforce, well, easily. Maybe you can, but it's a very complicated heuristic and complex masking. But as far as I know, and people in chemistry have been thinking about this a lot for something like SMILES, it's really hard to build kind of a unique sequence that describes one object. But another related question, I think, for GFlowNets in particular is that something that will be discussed a bit later is there's implicitly here some kind of backward allocations of the flow. Here, I kind of did something where everything is equal, but you could possibly train a network to say, no, I only want to care about one parent at a time. And then you'd kind of end up with pseudo true. But I don't know if anyone's investigated that properly.
Yeah, I have a good question about the concept of the flow because I come from the RL background. So for me, this kind of looks like just a value function, but your discount factor is set to 1. I was wondering if you ever experienced with, if it's possible to have a discount factor where your inflow is equal to like gamma of your outflow, like have this concept of discounted flows, if it breaks your training or not, and would you even be interested in going that path? Like, is discounting even relevant in terms of generating data?
I want to say no, but I think some people have thought about this more deeply than I. So I'll redirect you to them. So come see me after.
Thank you. Hi, thanks for the talk. I'm curious if empirically you have any observations regarding the number of samples needed for training relative to the number of terminal states in the problem. Is there any like relation there, or is it
the number of samples to like converge?
Yeah.
It's really problem dependent. I guess these are not cheap methods. Like training on a simplified fragment environment molecule, it can take, 6 hours to start getting decent results. And like I've trained model for days and they still have not converged. They're still learning and discovering new things. But I think it's really going to be problem dependent.
Thanks.
Probably last question, make it quick, maybe.
I was wondering, there's this assumption in making the composing the smiley face, for example. There's no difference in first doing the left eyebrow, then the right eyebrow. So what if there was a slight difference instead of there could be no difference
Right.
assumption, and there could be a large difference, in which case we wouldn't have a DAC. What if there was a slight difference?
Yeah, I mean, this is the case in like fragments. Depending on, let's say you're doing chemical synthesis kind of environments, depending on the order in which you do things, you'll get different results. That's true, and there's ways to handle that. You just have to represent your state in the right way so that when you give it as an input to the network, it knows that the differences are there. But yeah.
Very quickly, what is the trade-off in terms of how you split up your action space? So you could, for instance, have maybe like just a very like a large number of possible paths, but with like only a few actions, so few parents. Or you have a very complex action, so you have lots of parents, but you have kind of less states in your intermediate states. What is the kind of trade-off in training complexity?
That's a very good question. And I think this deserves more study because there are some cases where we've done that experiment. So let's say you're generating a sequence and you only have like 4 tokens. You could have 4 actions or you can generate 1 token, or 2 actions, or 16 actions generate 2 tokens. So you can think of all the lengths. And if you do that, there doesn't seem to be that much difference, which is surprising. But in some other environments where we're generating graphs, the way you give choices to the agent does seem to matter, sometimes very negatively if you're not careful. And I think that's something that should be studied more reinforcement learning, how to design an MDP.
Thank you.
No, I've already been introduced, so I don't need to introduce myself again. And can you see my screen? Okay. Yes, good. Here we are. So you get to hear from me about a lot of math. I hope everyone is very excited about this. So I will tell you about two different training objectives for GFlowNets. You heard about flow matching and how optimizing a flow matching objective at every state in a GFlowNet leads to getting a policy which can sample objects in proportion to their reward. And I will motivate and introduce two new objectives called detail balance and trajectory balance, which are the ones that we most often use in practice in applications of GFlowNets. And I'll conclude with some discussion of how to train your GFlowNet. Now, just to review and to set up background. Unfortunately, my figure is not animated, but this is the kind of figure that we just saw in Emmanuel's talk. We have a directed acyclic graph, which specifies the structure of a generative process. We have an initial state here labeled as 0, and we can follow the edges in the picture from left to right until we reach a terminal state, which is marked with a square. We think of the terminal objects as representing terminal states as representing completed objects like the molecules or smiley faces that we're trying to generate. And we learned in the last talk that when we assign a number to every edge, a flow, we can extract from this flow a policy, which is just as in RL, a way of getting a distribution over subsequent states when we're sitting at a particular state. The way we turn a flow into a policy is by taking the flows to all of the children of the state we're at and dividing by the sum. In other words, normalizing to get a probability distribution. So for instance, we may be at S0, so we look at a flow to S1 and to S2, and our policy goes to S1 or to S2 in proportion, with probability proportional to the flow to S1 and to S2, and so on until reaching a terminal state. What we're trying to achieve through any GFlowNet training procedure is to make the marginal likelihood that the policy will terminate in a given completed object proportional to its reward. And the main result that Emmanuel covered in the last talk is that when we enforce a local condition that at every state the flow in equals the flow out, the policy that's obtained from this flow happens to sample proportionally to the reward. And this is the first main theorem of GFlowNets, that if flow matching is satisfied at every state inside the state space, then the corresponding policy samples in proportion to the reward. So nothing new so far. But there are some problems with this objective, which Emmanuel already alluded to. So let's go through those. The first one is that it's a local objective. That is, the objective at a particular state depends only on the flows into and out of that state, not other ones in other parts of the state space. Now, when we perform an update at one state, we still might affect the edge flows somewhere far away. And that's due to the neural net parameterization of flows. So the flow function is given to us by a neural network. And so we change the parameters when we update the edge flow in one part of the graph. So it might affect the edge flow in another part of the graph. This is important for generalization. On the other hand, this locality still has a limitation. And this limitation is something that happens in other reinforcement settings as well, and it's the problem of slow credit assignment. I can illustrate it with this figure. So imagine that, so our graph is going top down here. So imagine that we sampled our policy, and we saw a very high reward state, this X at the bottom. And the flows on the edges along this trajectory were very small. So what will happen? Which edge flows will get updated when I got this very high reward state? Well, the flow matching might be very close to satisfied at all of the states in the beginning of the trajectory where their flows are small. So the only place where there's a discrepancy would be at the very end, where the inflow is small, but we got a high reward. So I should increase the edge flow there. So the only update happens near the end. So now this edge there now gets a higher flow through a gradient update. So now what has to happen to propagate this information about a high reward state closer to the beginning of the graph? Well, we have to see this previous state. And so until I see that state again, I won't get any update. So imagine I saw this state again. Now the outflow is high now, but inflow is still small. So now that one has to be updated, and the signal is propagated one step closer to the initial state, and so on. And if trajectories are long, and the likelihood of reaching these states is small, it can take a very long time to get an update to flows or policies near the beginning of the trajectory when we have an interesting state at the end. This is the problem of slow credit assignment, and it's a major limitation of GFlowNets with local training objectives. Now, another problem with flow matching, which Emmanuel also mentioned, is the possibly high computation cost. We usually, when we train models with flow matching, we have a model which takes in a state and outputs simultaneously the edge flows to all of the subsequent, all of the children of that state with a single neural network. Usually, actually, the model is outputting the logs of those states, but that's not what's important here. So flow matching is trying to enforce that inflow equals outflow. And computing the outflow is easy in this green rectangle. We just have to evaluate our neural net and sum all of the edge flows that it outputs, the flows to all the children. But computing the inflow is not so easy, because we would have to evaluate our model at all the parents of the state of interest. So if there are n parents, then to compute the flow matching loss, we need n+1 neural net evaluations to compute the loss. And for problems with many parents for any given state, this can be prohibitive. So that's a problem. We want to avoid that. And this observation is what motivated the introduction of the first loss that's not flow matching, called detailed balance. So I will introduce this one next. So the idea of detailed balance is that instead of working with edge flows, we'll introduce a different parameterization. So we will directly learn the policy, the policy, which is a distribution over children of every state in the graph. It's just like in reinforcement learning, it's output by a model which takes a state as input and gives us the logits of all of the possible actions, all of the possible children. And in addition to the policy, we need some auxiliary objects. So I'll explain them in reverse order. So we need a special object called the backward policy. And I'll talk a little more about what it actually means in a while. But you should think of it as a policy which can start at a terminal state and sample backward until getting to an initial state. So it's a distribution, or a model that gives a distribution over the parents of any state in the graph. And this looks a little funny because why would we ever want to start at a terminal state and sample backwards and get a trajectory that leads there? But this can actually be useful, as I'll talk about near the end. And in addition to those, we learn a single estimator, a neural net that gives us one number, a scalar, for every state, called the state flow. And you should think of this as, so when flow matching is satisfied, then flow in equals flow out. And they're both equal to something called the state flow. It's the amount of water flowing through the state. Now, how is this parameterization related to the one used in flow matching? So if we look at the forward policy and how it's defined in terms of the flow, so this bottom left here, the likelihood of passing to a child V from a state S is proportional to the flow from S to V. So it's the flow on the edge S to V divided by the sum of all the flows coming out. And similarly, the backward policy can be defined in terms of a flow. So instead of normalizing over all of the children, we normalize over all the parents. So to decide which parent to transition to, the backward policy takes the flow to all the parents and normalizes to get a distribution summing to 1. So if we look at these two equations, we see that there are two different ways to express the state flow just via algebra. The state flow is, on the one hand, the outflow of the parent times the forward policy, the likelihood, so the outflow at S times the likelihood of transitioning from S to S prime. And on the other hand, it's the inflow at S prime times the backward likelihood. So the backward policy's probability of transitioning from S prime to S. So the key part here is the equality of these two ways of writing the edge flow. We can visualize it also on the picture on the right, where these two quantities, inflow at S prime times backward policy, or outflow at S times forward policy, are both supposed to be equal to the flow on the edge from S to S prime. So now some magic happens, and we turn this equality into a training objective. So remember that we're learning F and the backward policy PB and the forward policy PF. So we take this equality and make it a constraint that we try to enforce. So the detailed balance objective for an edge from S to S prime is trying to make these two quantities equal. So this is just like the flow matching constraint, inflow equals outflow is turned into objective, log of inflow divided by outflow squared. We do the same thing here. And just like in flow matching, this we can stabilize this by adding small smoothing constants to numerator and denominator. And let's take a closer look at this last. So first of all, this is written as a log of some products and quotients, but because we're outputting flows in the log domain, and because we're outputting our policies through their logits, we can do some algebra and turn this into just a sum of logs squared. So it's just a quadratic loss in terms of the logits and the state flows. And let's also think about what happens at the terminal states. At the terminal states, we know that the inflow is supposed to equal the reward. And with the detailed balance loss, because the inflow and the outflow are the same thing as the state flow we're learning, we can just force that the state flow equals the reward at terminal states. So this is like a boundary condition that we enforce, in addition to this detailed balance objective, which has to be satisfied on every edge inside the graph. And from the algebra on the previous slide, we can see that if the detailed balance constraint holds on every edge, then the edge flow that we recover from it by writing the edge flow as state flow times policy satisfies flow matching. So by the first main theorem about GFlowNets, the policy is sampling proportionally to the reward. Now, this parameterization involves no edge flows. It involves two policies and a state flow. We can reduce the number of objects involved by fixing the backward policy to some simple distribution of our choice. I just want to note this here, and I'll come back to this a little later. Okay, so we have detailed balance, and it solves the problem of summing over a large number of parents because it depends only on a single edge. But it's still local, and so it still has the credit assignment problem that I discussed a few slides ago. So it would be nice if we instead had a trajectory level objective. That is one that sees a reward from a terminal state and immediately sends a gradient update to all of the edges seen along the trajectory. And we struggled with that for a long time to find such an objective. We first came up with it in the case of a tree-shaped graph where states only have one parent. And then eventually we had this realization that we can get a simple trajectory level objective, which I'll derive for you now. So now comes the mathiest slide of the presentation. So I promise it's only downhill from there, or uphill, depending on how you see it. So let's look at a trajectory. So it starts at the initial state as 0, and it takes n steps, ends at a state Sn, which I also call x. X is usually a terminal state. And let's write the detailed balance constraint on each edge. And I write it in this way, in the same form that it appears in the loss. So f times pf equals f times pb. So I write that the quotient equals 1 for all of those transitions. And Sn is a terminal state, so the flow at the terminal state equals the reward, R of x. So all of those equal 1. Now, let's take all of these constraints and let's multiply them together. So they're all equal to 1, so their product equals 1. So I've done nothing here, just multiplied all the equalities in the first line. Now, a lot of cancellation is going to happen because the flow in the denominator of one term cancels with the flow in the numerator of the next term. So all these flows cancel, except the very first f of s0 and the very last r of x, and we're left with this. So I've just done some rearrangement of terms. So let's look at this. So in the numerator, we have the flow at s0, and then the product of all of the policy's transition probabilities along the trajectory from s0 all the way to Sn. And in the denominator, we have the reward, and then the product of backward transition probabilities as we start from x, and then we go backward along this trajectory. And no other state flows survived. Now, that's pretty nice. So we have this so-called trajectory balance constraint, which says that this numerator and this denominator are equal. Now, I can also write it in this condensed form. So flow at s0 times a forward likelihood of that whole trajectory. Pf of tau just means the product of those transition probabilities in the numerator equals the reward times the product of all the backward transitions in the denominator. Now I write PB of tau given x because the backward probability of a trajectory only makes sense if I know where to start that backward trajectory at a given terminal state x. So when we have some constraint in GFlowNets, we want to turn it into a loss. Let's do that. For a trajectory, we just enforce with the same kind of squared log ratio trick. We enforce that these two quantities are equal. So the log of initial state flow times forward likelihood of the trajectory, divided by reward times backward likelihood of the trajectory squared. We're supposed to minimize that. So this objective is trajectory level. So it depends on all of the transitions and their forward and backward probabilities. So when we see a trajectory and we get a reward, we immediately get an update to all of the transitions that we had in the trajectory. So it's a global objective. Now, there's a theorem, and it's not exactly obvious that why it holds, that if we make this objective hold, so if we make f times pf equals r times pb for every trajectory, this is sufficient for the forward policy to sample proportionally to the reward. So the derivation I showed shows it's necessary because from detailed balance through this cancellation we get trajectory balance, but the other way requires doing some math. So practically, what do? We sample a trajectory from our policy or from some more exploratory version. You'll hear about that in the next talk. And we perform gradient updates on this TB objective. Let's take a closer look at what properties it has. Now, I've already said this is a global objective, so it leads to faster credit assignment due to yielding a gradient update to every state along a trajectory when a reward is received. In addition, it doesn't require learning the state flow for every state, for every state, only for the initial state, f of s0. Everything else canceled in our derivation. And just like Emmanuel mentioned before, the f of S0, which we do have to learn, at convergence ends up being equal to the total reward. So the sum of all rewards of terminal states. We use the letter Z to denote that often. Now, here's a point which is very important in understanding GFlowNets as a variational inference algorithm. The TB loss is actually doing something with a deeper meaning. So it's equating or trying to make equal two distributions, not over states, but over trajectories. One of them is the distribution over trajectories that you sample by starting at the initial state and then sampling the forward policy. The other one is the one that you sample by taking a terminal state sampled from the true reward distribution. Now, we can't usually do that, as we want to learn. And then following the backward policy from that state back to the initial state as 0. The trajectory balance objective is trying to make those two distributions over trajectories equal by making the ratio of likelihoods equal to 1. So one consideration that falls out of that is that we can actually fix the backward policy. So given a terminal state, we can just decide once and for all from the beginning, without having it learned, what is the posterior distribution over trajectories that will get us to that state. We can, for example, make the backward policy uniform. So that's a common choice because it often simplifies, it reduces the number of models we have to learn. When I'm just starting to prototype a GFlowNet, I often just start with trajectory balance with the uniform backward policy because it's very simple. If we fix the backward policy at every state to be uniform over the parents, then the only things we have to learn are the initial state flow and the forward policy. Very simple, right? So it's just like in reinforcement learning, where we just learn a policy, or maybe sometimes a value function, except we just have to learn one extra thing, which is the initial state flow. And a practical consideration is that this initial state flow we often learn in the log domain, and it often helps to set a higher learning rate on that because it can be trained stably even with a high, even with large updates. So just some results. As we saw, trajectory balance allows you to find more modes and converge faster generally than other training objectives. On the bit sequence task, here's a molecule domain where we first implemented and tested trajectory balance. So we get more stable training, more modes discovered, and so higher diversity and higher reward of the typically generated objects. Now, I want to conclude with some practical considerations about how to choose an objective. So you want to train a GFlowNet for your problem. You decided what objects you want to generate. You designed the state and action space. So you decided the generative process that you're going to use. So what objective should you use? Well, so I think that trajectory balance is a good objective to try by default because it's fairly simple to implement and it yields fast credit assignment. On the other hand, it has some limitations, which are that it can have a high gradient variance and a high memory cost, especially if the trajectories are very long or there's a very high range of rewards that you encounter. So sometimes you might want to try something based on flow matching or detail balance instead. Now, in general, detail balance does not work as well in settings that we often encounter, unless some special constraints are satisfied. There's a trick called the forward-looking flow parameterization, in which if you can compute some kind of proxy reward at not complete states, at incomplete states, intermediate states, then you can parameterize the log flow function, not directly through a neural network, but as an additive correction to this proxy log reward. And if there's interest, I can give a few examples of that in the questions. There are similar tricks possible if from every state it's allowed to terminate, which is the case in some generative problems. There we can also learn the flow function as a correction to the reward of that object if we chose to terminate there. And there's another objective called subtrajectory balance, which I won't go into, but which is a kind of interpolation between detail balance and trajectory balance. So trajectory balance learns from an entire trajectory by multiplying together the detail balance constraints and then canceling all the state flows. Detail balance learns from a single edge. So subtrajectory balance does this, but takes a partial trajectory, starting not necessarily at S0, ending not necessarily at a terminal state, and performs this cancellation so that only the state flow at the start of the subtrajectory and at the end are remaining. And combining the detail balance, edge level, trajectory balance, full trajectory level, and subtrajectory balance for partial pieces in the appropriate way can give us the best of both worlds in terms of stable training with the low gradient variance coming from detail balance and fast credit assignment that comes from trajectory level objectives. So I will finish with that, and here are the main references for the losses and ideas I've discussed. And you can check out any of those if you're interested. Thank you. We're a little behind schedule, but we have 5 minutes for questions.
Hi. Yeah, thank you for the nice presentation. I have a question about how to choose how to get samples. So I remember that in the training process, Emmanuel mentioned that policy could be off policy, but in practice, which policy do we should choose?
That's a good question. So we know that for the forward policy to sample proportionally to the reward, trajectory balance or detail balance or flow matching has to be satisfied at every state or at every edge or at every trajectory. So we are actually free to choose any training policy we like as long as it has full support. Now, what we do in practice, this is the subject of the next presentation, but just to give you a preview, common techniques are some modification to the on-policy training, like introducing random actions or tempering, as well as using information about known terminal states, such as those obtained through a replay buffer. So if we have interesting terminal states, we can train on backward trajectories sampled from them. But you'll hear more in the next talk.
Thank you. Can I ask another question? How can we choose the length of sub-trajectory in practice as well?
For sub-trajectory balance?
Yeah.
Well, that's an interesting question. I don't know the best answer, but what we did in the paper on sub-trajectory balance is we took all of the sub-trajectories and we weighted them in proportion to some constant lambda to the power of the length, which is inspired by a technique called TD lambda in reinforcement learning.
Okay. Thank you.
Considering the trajectory balance objective, you said that sometimes common practice is to set the backwards policy to a uniform. I have a hard time understanding how this wouldn't just enforce the forward policy to also be uniform. How does this actually let us still sample proportional to the reward?
Well, first, the theoretical side of that answer is that for any backward policy you choose, there's a unique forward policy such that together they optimize the trajectory balance objective. Now, how do we understand that? So we think of TB as equating two distributions over trajectories. So let's start with this backward distribution. We can sample it by taking a terminal state from the reward distribution, which imagine Oracle can sample for you, and then sampling uniform backward policy. So that distribution over trajectories can also be sampled forward. And if those two distributions are equal, then their marginal distributions over the terminal state are also the same. And for the backward one, by construction, it's the reward distribution. So for the forward one, it has to be the same.
Oh, I see. Thank you.
And yeah, I suggest you can read the paper on GFlowNet and variational inference for a discussion of this.
Thanks for the talk. I guess my question is, what if you cannot enumerate the parents? Like if it's just too difficult? Because even for the backwards policy, I guess you have to know how many you have.
Yes. So the question, as I understand it, is even if you're fixing the backward policy to uniform, so 1 over number of parents, you still need to know how many parents there are. And no, if you have never gotten your hands dirty with GFlowNets, it might not make sense why that can even be a problem. But in fact, it can be. For example, in molecule generation, when there are many ways to remove a component from a molecule, you may get possible parents which are equal due to isomorphism. So there are different construction orders for the same molecule, and it's a difficult graph isomorphism check to determine if 2 ways of expressing the same molecule are actually the same. So, well, there's nothing you can do about that. You have to do an isomorphism check on the parents. I don't have a better answer. Okay, you can do faster isomorphism checks if you learn if you have a learned hash or embedding for the parents, which allows you to quickly determine if two molecules are isomorphic.
But yeah, that could arise in other settings where hatching a graph is not necessarily the answer. It could be also in domain uncertainty of. But anyway, so I guess the answer is you can't. You have to find a way to enumerate the parents.
Okay, in that case, we will have our next talk. So let's take a break until 11:05. Yeah. Get your bio.
Or just share screen.
Yeah, share screen. Okay, let's resume. Doesn't work, does it? Okay. Right. Before we continue to the next talk, I have an important announcement. So after this talk, we're going to have a practical session. And for this, you will need to, if you want to run some code on your own device, you need to you need to download some code with environment and some prerequisites. And I just want to let you know that the links to those are now posted on the GFlowNet.org/schedule, the page with the schedule of the workshop. So you can download that and prepare for that practical session. Right, that was the important announcement. And now let me introduce our next speaker, Jared Rector Brooks, who is a PhD student at Université de Montréal and Mila, and co-founder of the molecular design startup Dreamfold. He's, as a PhD student, supervised by Yoshua Benjo and Sarath Chandar. His research interests span generative modeling and probabilistic inference with applications to protein binder design. And he will tell us about the practical side of training GFlowNets.
Thanks, Kolya. Hi, everybody. So I'm going to talk about what Kolya said I'm going to talk about. So let's talk about it. Okay, so GFlowNets. GFlowNets are an interesting thing we've talked about. There's a lot of parallels, or there's a lot of connections between RL, generative modeling, and GFlowNets. These come in forms like Kolya mentioned earlier. There's deep connections between variational inference and GFlowNets. And in particular, the way we train GFlowNets is very similar to reinforcement learning. In reinforcement learning, right, we have an MDP. We take steps sequentially, and we get rewards over time. In GFlowNets, we do about the same thing. We have some MDP, something which is saying, at least in the discrete space, we have an MDP, something that's saying, from this state, I can take these actions, and I'm going to transition to these other places. And specifically at the end of an episode, at the end of trajectory, we get some reward. So generative models also not really like this. We train them very differently, but they kind of, in a way, do a similar thing, where you have data set instead of having not a data set. But you train them to match a target distribution. And specifically, in the variational inference case, you can recover some very similar things to what we do with GFlowNets. So as Emmanuel and Kolya already mentioned, there's really a core training loop of what we do for GFlowNets. So it's pretty simple. It's just like RL, right? So the first thing we do, we have some policy and we say, okay, policy, let's generate some experiences. So we get this batch of experiences somehow, and then next we're going to get some rewards. A GFlowNet is all about the terminal rewards, right? What GFlowNets do is they sample objects, as Emmanuel was talking about, proportional to the reward of those objects. And so these objects, we say, are basically the states we arrive at the end of a trajectory. So we generate our batch of experiences from our forward policy, and we get some rewards for the objects that these trajectories generated, and then we compute the loss on these trajectories. And so here, I'll make a quick note. This notation is a little bit different. I'm saying that we're sampling a trajectory from the forward policy, which is the same way as writing the same thing we had before. If we recall that a policy is a Markovian policy, then the likelihood of sampling of a trajectory is just the product of all the transitions in the trajectory. So this is the core training loop. Cool. Basically, the first and third part are very interchangeable. So Kolya was already talking about what do we do for step number 3. There's a bunch of different objective functions. All of these try to do the same thing in principle. We have a set of constraints for GFlowNets, and we want to try to say that everywhere in space, at all different times, these constraints are satisfied. Because if we do this, then we get what we want. We get a sampler that samples objects proportional to the reward. So that's one side of things. The other side of things is how do we actually choose, how do we get the data that we're going to use to train our GFlowNets? And so what we're going to focus on in this talk is specifically how do we get this data, how do we get the things that we're going to train our GFlowNet on? So how do we do this? There's 2 main levers. The first lever, as people have talked about, is how do we generate this data, right? So just like in RL, we have a policy, we simulate the policy to get back experiences. We can choose how we want to generate these experiences. We can change our policy, we can do different things to make it more exploratory, or maybe make it focus on specific modes more. And so we have ultimate freedom really to choose how we want to do this. This goes back to one of the core important things of GFlowNets, which is that because of the way the objectives work and the way the math works out, you can train them off policy. You can get samples, you can get data from wherever you want. If you train everywhere, you will get a sampler that does what you want. Of course, we don't sample everywhere, but the point is you don't have to sample as in VI, as in variational inference. What you typically, or what you might have to do is you generate things according to the thing you've already learned. And now if you want to go away from this, you have to import and sample, and this is sad. We don't want to do this. It's unstable, it's not as fun. But because of the way the GFlowNet objectives work, you don't have to do this. You can sample wherever you want, just as long as you try to satisfy detail balance or flow matching or trajectory balance or whatever other balance, you're happy. So this is one lever. How do we choose what, how do we design a policy? How do we get a policy that's going to help us discover modes, which is important, right? Like this, especially as you scale the problems, as you move the problems from, the toy, like real world tasks to really big real world tasks, right? Like the thing that I'm interested in is protein design. And for some of the proteins that you might want to generate, like they're say 200 length long and there's 20 amino acids. So how big is that? That's a search space of 20 to the 200th. This is hard to explore. It's just hard. And also there's other hard things, right? I mean, you could imagine having a very non-smooth reward functions, which is something that we want to do sometimes, right? Sometimes we want, what do we really want? Like if we're doing a search problem, we want to generate the best things, the best molecules or the best proteins or the best crystal structures. And we want to generate a diverse set of these. But to get the best ones, you have to sample, GFlowNets are going to sample proportional reward. So you might have to make your reward function rather non-smooth and more peaky to try to sample more often the things that are really good. But the more peaky your distribution is, the more likely you might be to get stuck in modes and get mode collapse and be sad. So we should figure out a good way to do this. And we've done a bunch of things. The second thing is that now once we have the data that we've generated, how do we choose, even from the data we've generated, which things we actually want to train on? So this is stuff like Emmanuel was mentioning earlier, replay buffers. How do we choose of the data that we have, which things we want to use? And depending on the way we do this, you can see rather significant differences in how fast you train, but as Emmanuel said, with caveats. All right, so designing an exploratory policy. So let's say we have a target policy. This is our PF that we've talked about so far today. And this thing is like your normal GFlowNet policy, right? It's trying to, it's going to try to satisfy detail balance or trajectory balance, and it's going to try to sample proportional to the reward at the end of the day. So we can also have a behavior policy, just like in RL, whose job is just to generate samples that are good for PF to learn on. what do we want? We want something that learns the distribution. We want to be able to sample from R. So all we care about is, can we get a behavior policy, which is going to make learning to sample R as easy as it can be for the target policy. There's a bunch of considerations here, right? But one main thing is we want to try to have the behavior policy be, we call full support over the object distribution. So you can imagine if you do not have full support. So what do I mean? Like, let's say we have this grid here, right? And we have a behavior policy which ends up kind of saturating in some way, and it only samples the top left corner. If you show this to a GFlowNet, it'll be perfectly happy. It doesn't care. Like, it will see I can go to these 4 states. Okay, cool. I'll learn my Z and the trajectory balance to be the partition function for those 4 states. It'll learn PF and PB according to that partition function, and the loss can go to 0 everywhere, and the target policy will never sample anything besides those 4 states. So we don't want this. So we want to make sure we sample everywhere. And as long as we have some likelihood that we're going to sample everywhere, at least in theory, eventually we should converge to a true correct GFlowNet policy. Of course, this doesn't necessarily happen in practice, but in theory, it is true. Okay, exploration for GFS. Okay, obvious first try. What should we do? Let's just take the current target policy. But this is dumb. Don't do this. I mean, it could be okay, but like in general, it's not great. So like I was saying, same thing. You could imagine you have like your current target policy, it isn't constrained to sample from everything. And so we see this happening here. We have this true distribution where it's very peaky. These corners, there's 3 corners that have some reward, and the GFlowNet's going to start from the top left corner. And it's perfectly fine for this GFlowNet to just go and find one mode. And you can pretty easily see, I mean, you can train this yourself and you'll pretty easily see that the loss goes to 0. But what happens is it just learns to generate maybe one of the modes. And even within the mode, it's not even capturing all the other states that are right next to it. It's perfectly fine to just saturate and mode collapse. And this is kind of expected. There's an interesting little proof in the GFlowNet and variational inference paper, which shows that if you learn specifically with trajectory balance on policy, the gradient you get is the same as the gradient of the reverse KL. And we know from generative modeling, this is not a good thing to do. The reverse KL has problems with mode collapse, and you see exactly the same behavior if you do on policy learning in GFlowNets, as you would in RL as well. So a second try, we can do some rather simple things that interestingly seem to work in many cases. So just like in RL, we can mix in uniform noise with the current policy that we're learning. So the most obvious example of this is to take an epsilon random policy, just like epsilon greedy in RL. And so we say that with likelihood 1 minus epsilon, we're going to sample an action from the target policy. And with probability epsilon, we'll just take a random action. The other version of this is really the way that we use GFlowNets in practice is that we, as many other things, learn the log its, and this gives us a Boltzmann distribution. And so as in other Boltzmann distributions, you can learn a temperature which controls how peaky or how flat this distribution becomes. And so we can use this temperature parameter, whereas if you increase the temperature, if you increase the temperature, the policy becomes more flat. And if you bring that temperature to 0, it becomes very peaky around the thing that it thinks is best. And so one approach is to just take a policy and take the logits that we learned for the target policy and temper the distribution with some like value of temperature greater than 1. To basically have a slightly more flat distribution than the target policy. And these actually kind of work rather like surprisingly well. most GFlowNet papers use this to date. I mean, we've run experiments where at least in small scales, for example, in small scale settings, these work really, really well. Like it's hard to beat this, like in smaller scale settings. Even as you scale, like there's an interesting experiment we did at some point where we had, it was an RNA generation task and you have about 20 million states. So not near as big as, 20 to the 200th, but 20 million states. And with this exploration, the GFlowNet finds every mode that exists very quickly. But this has failure cases, as you might expect, specifically as the reward becomes more sparse. So like I was saying, if the reward basically becomes less smooth, or if the search space is very, very, very large, these things can start to fail. And so this is learning with a tempered policy on the same problem as before. And just as with an on-policy distribution or on-policy exploration policy, mode collapses and goes to one thing. So how do we avoid this? We don't like this. This is sad. There's some ways to do this, right? I mean, you could imagine in this case, right? Like you could even game it with these, right? You could have a fully random policy. Like this would be fine. This would work. You could have a fully random policy, or you could bring the temperature very, very high, which people also do. This is a typical thing that people do in MCMC, for example, with replica exchange, where you have many different MCMC chains, all at different temperatures, and the higher temperature ones, higher temperature MCMC chains are more likely to sample everywhere in the space, and you can kind of mix these things. So there's a recent GFlowNet paper that is doing something similar with temperature, with choosing the temperature of the tempered policy. But there's other approaches that people typically use in RL, and we'll cover briefly two of these approaches. So first, something that's very useful in RL is to try to use intrinsic rewards to encourage exploration. So a paper in iClear 2023 tried to do this with GFlowNets. And so basically we use a pseudo count to augment the reward of the terminal state. And so basically we change the reward such that for places we have not visited, the GFlowNet is incentivized to visit them more. And as it visits more and more, the reward goes down and the GFlowNet is less likely to sample this. So this paper in particular uses RND, which is a way to do pseudo counts in RL, and works rather well, specifically when we have a very sparse reward. So here is, this is two results. On the left, they take a very, very sparse grid. And in this case, this sort of intrinsic reward approach works very well. Very similarly for molecules, they use a sparse version of the molecule task. This also works very well. There's other things you can do, right? Another RL exploration paradigm is to use uncertainty, and there's much work on this direction. And so this also works in some cases if the search space is very large, or if it is sparse as well. And so what you do here is very much like bootstrap DQN and RL. You keep a ensemble of policies. At each step, you choose a member of the ensemble and generate a trajectory according to this member of the ensemble. You can encourage diversity in multiple ways in the ensemble with bootstrapping or prior networks. But this is like, these are two versions of these things. This is a general recipe, right? Exploration for GFlowNets isn't that much different than an RL. There's many ways to use uncertainty to give better ways to explore in RL. There's many ways to use intrinsic rewards. There's many ways to do exploration besides these things in RL. These are all things that probably will work, probably will be very useful. They haven't been tried. And so if people are interested in this, they should try. These are good things to try. So yeah, if the exploration problem is a bit harder, if the distribution is maybe not so easy to generalize to, for example, Thompson sampling works well. There's other things we can do. Say we have a data set, say we know some really good samples, we can take one of these really good examples, X, and we can we can sample a trajectory from our backwards policy and train on that trajectory. And this has been very useful in a bunch of different papers from back in 2022 on energy-based modeling with GFNs, doing EM with GFNs, also doing things for making exploration better with MCMC. This also works there, where, for example, you take something that is close to a mode, you do a small chain on it to get a really even better sample, and then you train on the backwards trajectory that you get from those very good samples. And like I said, you can also play with tempering the reward distribution, as in replica exchange, for example, or the temperature conditional paper. So what things should you do? It's the first rule is just don't do one policy. Like this is just don't do this. But besides this, it's not so clear. You just start basically. I think the easiest thing to do is just start out with epsilon noisy or tempering. This works for a lot of settings. Like it really works for a lot of settings. For things that are getting harder, you might need to start being a bit more smart. Maybe try something like JFNs or Thompson sampling. Or if you're feeling brave, try your own new like uncertainty method or intrinsic reward, or take something off the shelf from RL. It might work. If you do have a data set, you should use it. Mixing and training trajectories sampled from backwards policy is quite powerful and is very useful if you have access to samples, which in some cases we do. All right, so that is exploration. Now, what is the next thing is we have data. We've generated a bunch of data from our exploratory policy. How do we choose what data we're actually going to train on? So let's say we generated a batch of trajectories from our behavior policy. How do we choose which of these trajectories to train on, right? So there's been a bit of research into this, and right now there's basically three options. The first is just don't use a buffer, just take the batch of trajectories, train on it. Second, that people do commonly is take a standard like uniform first in first out buffer as an RL. And the third thing that people have done is take, again, a first in first out buffer and try to prioritize based on reward. People have also tried a bit prioritizing based on the loss, but I think the results on this are a bit less well-founded at this point. So reward prioritized buffers. This is from a paper with Emmanuel and Nikhil, and also in a paper with Andre Nika from 2022. And so here the idea is we have a batch, or we have a bunch of trajectories and states in a buffer, and we can try to prioritize those states which have higher reward, and train on these more than other things. And so the specific scheme that most of these reward prioritized buffers have done is basically take the top alpha quantile of rewards or objects with rewards in the buffer and choose beta % of your training batch from this and 1 minus beta % from the rest of your buffer. There's other ways you can do this. You can just sample proportional to the reward in the buffer. These things also can work, but this can be pretty useful. Specifically, it's been found in, for example, Emmanuel's paper that basically if you do this, you will converge to a good value, perhaps faster. And in some of Nikhil's work that you can discover more modes, but it does come with caveats, right? You have to be careful with how you're doing this. If you do this naively, if you make it too, in a sense, greedy, choose too big of a beta, or make the top % too small, say you're only training on the top 0.5%, you can run into a very myopic policy. You can end up with mode collapse again. And so there are things you can do. You can try to, you could try to add in some measure of diversity in how you're doing this, maybe in your insertion strategy, or in your sampling strategy from the buffer, or you can just play with the hyperparameters, but you have to be careful. I mean, imagine, right? Like if you're just choosing the best things, you're just going to keep choosing the best things and you might mode collapse. So this can be very useful for training. Just make sure you're not doing the wrong thing. Just make sure the things you're doing or the results you're getting are making some sense. Okay, so wrapping up. For exploration, what should we do? Steer away from doing on-policy learning. Start with just simple exploration things, just like in RL, do epsilon noisy and tempered things. If this doesn't work, try out more RL-like exploration methods like GFlowNets, which try to do intrinsic rewards, Thompson sampling, which tries to do uncertainty, or genuinely you could try many different RL things that people have done for uncertainty, and it may work out pretty well. For replays, uniform buffers don't seem to help all that much. There's been some results on this. I think just in general, people have not seen a huge difference between just using a uniform buffer, versus just training on the batch of trajectories you've generated. Perhaps if you try to add in some things around diversity, you might get some better making sure you're not like forgetting modes. But just vanilla uniform FIFO buffers don't seem to help much. But prioritized buffers do seem to help. So try them. Just make sure you're not doing something that's making your policy die. So yeah, happy training. A couple quick helpful things, just small things that can make a big difference that are not related to exploration or replay buffers. So stabilizing learning. This can be a big deal, especially as your rewards become very big. So for example, if we want to do search, we want to make some of our rewards very big, especially if a very big search space, you have to do it. Otherwise, you just won't sample even if your GFlowNet converges to the right thing, it won't sample what you want. So you, in some cases, just need to make your reward very, very non-smooth for search to work. And so in these cases, you can start running into issues with stability. Gradient clipping is critical on some problems. You might have to play around with hyperparameters. Using delayed network can help training. So using EMA on exponential moving average on model weights can be useful. There's recent work on target networks to help stabilize things, and so on. Another thing that I forgot to put on here, and I'm just remembering, normalizing the reward, making sure, trying to get your reward into as nice of a scale that you can under the constraints that you have can be quite important. And another trick we've found that can sometimes help a lot when specifically you have a very low reward temperature T. So this means basically your reward is going to be very spiky because you're dividing reward by this temperature, right? So maybe it's 1e-5 or something. And so it means your reward gets very spiky. Rescaling the loss by the temperature to some exponent, maybe 1, can be critical for not making everything blow up. So yeah, that's it. If people have questions, I am happy to answer them.
I have a question about the exploration strategies you talked about. You briefly mentioned count-based exploration and random network distillation. Usually these techniques assign a reward at the current state, but for GFlowNets, we only assign rewards at the terminal state. So my question is, if you have a trajectory, do you estimate that exploration reward along the trajectory, or just the terminal state, or at every state and then for propagated?
You can. Actually, in the GFlowNet paper, one of the contributions is to be able to use intermediate rewards and help this for sampling. So you can do this. It might help your problem. I think it's problem dependent if it helps versus even just using the reward or count-based exploration on the terminal states. But you can do this. If you're interested, check out the GFN paper.
Thank you.
Mm-hmm.
I was just wondering, which methods would you prioritize in a situation where you know in advance that all the trajectories you have available for training start wrong?
Something exploratory, I suppose. Something exploratory. I mean, you could start out with something with a very large value of a very exploratory epsilon noisier tempered policy. You can, I mean, all these exploration things have hyperparameters that control how exploratory they are. Like I would start with higher, and you can always anneal your exploration parameters down as you go. Like, so start high, be exploratory, and then.
Hi. Like when I think in this slide, in this session, like you assume that reward functions are kind of known, right? But
Yes.
let's say like reward functions are unknown and we need to learn from data. In that case, like should we add more bonus term, like coming from a certainty of like unknown reward functions?
That's an interesting question. I'm not sure I have a good answer. So you mean like inverse problem settings, or are you thinking in like energy-based modeling settings where you're trying to learn an energy?
I'm just considering a kind of setting when our reward is unknown and we need to learn from the data.
I think it's not, at least to me, it's not clear. I would say try things. Try a bunch of different values. Maybe Kolya seems like he might have an idea. Yeah.
If I may make a little comment on that, I've seen a few settings where you learn the reward, either because the reward is given by likelihood under a generative model or as an energy-based model, where your estimate of the reward function starts out really smooth. And when the reward function starts really smooth, it's easier to learn the policy to match it. And as the reward function evolves and becomes spikier, it becomes harder to explore. And in this setting, actually, exploration is a lot less important because it's easier without exploration to match a very smooth reward function. And as the reward function becomes peakier, you gradually settle into the modes. But I suppose it always depends on the specific problem at hand.
Great.
Can I ask another question? Like, I remember that so like there's a kind of analogy for like Q learning and also like flow matching objective, right? And are there any like the similar concepts to like which are analogous to like a policy gradients stuff?
I think there is actually a very recent work. Somebody else might be more familiar, but I think there was a recent work submitted to iClear maybe on policy gradient with GFlowNets. I think there's recent work on this. If you look it up, it should be around.
Okay, thank you.
Thank you, Jared, for the talk. You mentioned earlier that there was this connection between TB and reverse KL. Is there a similar connection that you're aware of for replay buffers between a different divergence?
Different averages?
Different divergence, like for example, I don't know, like that it's not purely like a reverse scale anymore, right? It would be like some different divergence, maybe like a mix between forward and backward, or some maybe.
Yeah, we've thought about this a bit. I mean, I think so, right? I mean, you can imagine you try to do importance sampling from your buffer, and then you could say, I have the forward like KL, but then of course you have to importance sample. Like, there might be interesting ways to. Maybe Kolya has thought about it. We can talk about it after. There might be interesting ways to try to think of like other divergences besides, something where you have to importance sample. Maybe you do have to importance sample. I don't know. I think I have tried at some point some importance sampling experiments, but I don't remember what happened with them.
Thanks.
Yeah. Cool. Great. Well, thank you, everybody. May you train GFlowNet well.
Right, so next we have our first GFlowNet practical session. And Is Joseph here? Oh, yes. You have to come up here so I can introduce you. Let me introduce Joseph Viviano, who is a machine learning scientist at Mila, working on research tooling and applications of machine learning to biological discovery. And he will lead the first hands-on session on training GFlowNets. Now, there will be a few of us walking around the room to help out for anyone who needs help.
Thank you. Just let me get my screen set up. But in the meantime, on the schedule at the top of the second day, you'll find links to collabs for the 2 sessions, as well as a link to GitHub if you prefer not to use Colab for some reason, where you can download a notebook onto your computer and run it locally. Also, there's a bunch of TAs, quote unquote, in the room. There's going to be sort of a fill in the blank style exercises throughout this. Could all the TAs quickly raise their hands so that the rest can look around and see who they are? We've got about 7 or 8. Okay, so what I'm going to do is sort of talk us through this this notebook, which is kind of designed to be read alone, actually. So I won't necessarily read every word. But every time we come to sort of a interactive portion, I'll give you around 5 minutes to sort of read through the code and fill in the session, and you feel free to grab the TAs who will be wandering around during those moments. So the first thing that you need to do would just be to execute the top cells to do your imports and define some helper functions. This exercise is going to be building off of what Emmanuel Benjo presented this morning, where we essentially want to generate faces. We want to sample faces more often when they're happy than when they're sad. So I'm just to walk you through sort of how we would parameterize this. This is a very simple feature space. We're going to be sampling features one by one, and a face is going to be given as a set of features. So we'll have smiles and frowns, and then eyebrows of different orientations. And if you were to, maybe I'll pause before I keep going. Is anybody not able to get something running? Feel free to just raise your hand. Okay, everybody is on board. One? Oh, you don't have a laptop. Okay. All right. Okay, so great. What we're seeing here are examples of faces. So we have, a happy face here, which means a smile, and an eyebrow, one for each eye. And then we have some invalid configurations. For example, multiple mouths overlapping. That's not good. We don't want multiple eyebrows either, and we don't want faces that are missing eyebrows in particular locations. And so what we need to do if we want to sample faces, as you, I think, know already from this morning's session, is we need to define a reward function such that we're going to sample proportionally to that reward function. And just to prove to ourselves that what we're doing is working properly, we're going to give twice the reward to a happy face than to a sad face, so that we can observe whether our model is actually sampling happiness more often than sadness. And we also don't want to sample invalid configurations at all. So we're going to give those configurations a reward of 0. So here we have some functions that are simply checking whether our feature list contains overlapping features, which is bad. And then we use that information to calculate our reward. So we'll give 0 reward to overlapping features within our data set. I'm sorry, our features. And we'll give higher rewards to happy faces than sad faces. And as we looked at earlier this morning, you can sort of see all the possible paths we could take as we're constructing faces, sampling these features one by one to construct our final object. This is essentially the space that our GFlowNet is going to be traversing as we train it. So each iteration of this is essentially an iteration of our training for loop. And so just to quickly reiterate the flow matching condition, which was already covered now twice this morning. Basically, what we want to do is we want for every state to ensure that the flows entering that state and exiting that state are equal. And this is the loss function that we're going to be using to train our neural network. And as an aside here, because I know that this terminology is overloaded, network does not, in the GFlowNet terminology, is referring to the MDP that we're traversing. So we have a function approximator that's predicting the flows, that's giving us the probability that we're going to sample each of the next actions. And then we also have this network of flows that is implicitly learned by the GFlowNet, the function approximator. As we've covered earlier, of course, the goal here is to sample these configurations proportional to the reward. So the first thing that we need is that function approximator. And this could be really simple. It's going to be some kind of MLP with a hidden layer that's going to take in our input state, which is going to be the presence or absence of the 6 features that we've defined already. And then we're going to be predicting one of 6 actions, which is which thing should I add next to my state. And since we want our flows to be positive, it's important here that we're going to exponentiate the output in this particular case. So here we have our objective function that you've seen before, where you have essentially you want the flow incoming to a state to be equal to the reward plus the flow outgoing to the state. Now, why would I say this? The reason is because at the terminal nodes, you have only a reward, you have no outgoing flows. Otherwise, you have no reward, you only have outgoing flows. That's why this works. Okay, so the first sort of key exercise is for us to be able to figure out what the parents of a state are in order for us to be able to calculate this. And for this, you're going to need to know that we're representing our feature keys. This is often used within the code, which is simply a list of strings that's used to represent the set that becomes your state. So in this cell, what you should do is figure out what the parent states are of a given current state and which actions led to the current state. And the way I'm going to do this is I'll give you a few minutes and then I'm going to flip to the answer like a cooking show. So that nobody gets left behind if there's something tricky. So I'll give you all a few minutes now. So I'll draw your attention to the screen. Here, what we're doing when we're calculating the parent states is we're essentially figuring out if there's a parent that exists that has all parts except for a part that's currently within the list, because something must have been added in order to produce this current state. And then similarly for the parent actions, we're simply, it's just the addition of any of the current features would have produced that state. Now, of course, this is an exceedingly simple example. I think that one thing to note here is that in very complicated spaces, the logic here can actually be quite heavy. This might take a reasonable amount of thought in order to implement. So I'll just give you a moment. I'll move on. So now that we have the ability to calculate our parents, the other piece that we need is to be able to calculate our loss itself. So I'll give you a moment here to implement the flow matching loss, which takes into account the incoming flows to a state and the outgoing flows and the reward. So just to confirm, I've put the answer on the board for this one as well. Hopefully straightforward, so we can move on to the training loop, which is a little bit more involved. But it's important to run this next cell here, which is going to define the sort of fixed hyperparameters that we're going to use for training all future models. The reason why is because I wanted something that could train quickly on a laptop or something like this, and we're going to be comparing different configurations on models that can train in say a minute or two. So if your models are taking longer than a few minutes, then something's wrong. We can see the difference in the results after we do this. So if you can run these hidden cells in order to produce this text, and you'll know that it's working. So now what we're going to do is we're actually going to instantiate and train our model. So we're going to let the model generate its data by following its policy, and then train on that data. And once again, the state is a list of strings representing the keys in this feature keys variable that we saw before. And there's a function here that face to tensor that's going to take that list and turn it into something that PyTorch likes, which is sort of a Boolean vector. So I'll walk you through this training loop, but hopefully it's fairly straightforward, but there are multiple lines that you need to fill in as we go through. So what we're going to do here is, for each episode, start with an empty state, and then predict the flows for that empty state. And then we're going to enter into a trajectory of length 3. Why? Because we're trying to add 3 things to the face, a mouth and 2 eyebrows. So we're actually making the problem a little bit easier, because if you wanted, you could set up the problem such that the model would have to predict when to exit. But since we already know that we only need 3 things, we can build this directly into the training. Then what we need, I'm looking at the wrong thing. Pardon me. Then what we need is to sample an action and compute the new state. So we need to calculate our policy, and then we need to sample an action from that policy in order to calculate our new state. Recall that we're concatenating strings to a list in order to represent our states. And then what we're going to do is we're going to compute the loss. So we have to enumerate the parents and then compute the flows of each parent. So in order to do this, we need to use the function we defined before. And then we're going to get all of the parent states, and we're going to collect their flows and index the correct flows to the current state. And then at the end of the trajectory, we're either going to collect our reward and edge flow predictions, which are going to be different depending on whether this is a terminal node or not. And we can finally calculate our loss using the function we defined before. The rest of this is just bookkeeping. So if I'll give you a few minutes now to go through this and fill in the blanks. Hopefully you didn't get all the answers already by my mistake. And you should be able to train this cell, which will produce training curves that might look something like this. And we can see what you got after the fact. Don't be afraid to ask questions. There's lots of, if you need help. Who has a training curve? A few? Okay, like 10%. I think I'm gonna flip to the answer just in the interest of time. So what we want to do for calculating the policy is we just want to normalize the edge flows by their sum so that we get a probability distribution. And then we're going to feed that into a categorical distribution with the probabilities being the policy, and we're going to sample from it to produce an action. And then that action is going to be used to index into our feature keys list to produce our next state, which is just a concatenation of the previous state plus this new string. And here we're going to calculate the reward if it's the end of a trajectory and set our outgoing edge flow predictions to just 0 so that it will sum over 0 in the loss. And then we'll do something the opposite otherwise if it's not the end of a trajectory. So we'll set the reward to 0 for an intermediate state, and we'll predict the edge flows using this new state to continue the loop. So maybe I'll give you a moment to fill these in if you want. After you do this, you'll be able to produce a training curve that'll look a little bit unstable. That will produce, if you run this function check sampled faces, which is one of our hidden functions, you'll see that we're doing okay. We're getting like a decent number of valid faces sampled, and we're getting roughly the correct ratio of happy faces, although not correct. What we can do is we can actually visualize the flows that are learned by our function approximator. And there's a few things that are interesting to look at here. First of all, you can see that the flows are clearly lower for the invalid configurations, and also that the magnitude of the flows is higher in sort of early regions of the MDP, which is common because we're sort of distributing this probability over more and more transitions as we go deeper. If you didn't get what happened before, that's okay, because we're going to redo this again with most of the functions filled out for you. So don't feel like you'll get blocked. But I will pause here to see if there's any sort of like major questions that, because maybe multiple people have them. Okay, in that case, the last thing I'll mention is that as we saw before, the flow of the initial state is going to be an estimate of the partition function. So we can actually pull that out here by just feeding an empty list to face to tensor and passing that to our function approximator. And we'll see that our partition function is not correct. It should be 12 because we have 4 good and 4 bad, 4 happy and 4 sad faces, and we have twice the reward for happy. So we've done something wrong. I mean, what we did wrong was that we didn't train for long enough. But actually, we've done a bunch of things wrong. This is a very naive implementation. And one thing that we could do that would make it much easier to learn this would be to prevent the model from making bad decisions in the first place. Because we know that adding 2 eyebrows on top of each other is a bad idea, or 2 mouths on top of each other is a bad idea. So what we could do is we could mask those actions during the sampling of the forward path and sampling of the forward trajectory. And this is a very, very common trick that's done when training GFlowNets on anything that's of a reasonably challenging scale, because you're wasting a ton of time sampling bad configurations and learning not to sample them if you don't do this. So, oops, I'm gonna go here again. What the next thing we need to do is to figure out how to prevent the model from sampling bad configurations. And that's going to be done using a simple Boolean mask. So the goal here is to calculate from the current state what the mask should look like for the next iteration. And in order to do this, you'll need this feature keys list, the indices of it, basically. So why I have this printed here for you. So I'll give you a moment to try that out. All right, I've thrown the answer to this one up as well. So because of the construction of this this list, it's we're basically just masking the first two elements if there's already a mouth present, the second two elements if there's already a left eyebrow present, and the final two elements if there's already a right eyebrow present. And then the real question is now that we've calculated this mask, what should we do with it? And so here what I've done is I've given you the same training loop now with sort of the most of the elements filled in for you, but you have to use the mask in order to prevent the model from sampling bad configurations during the forward trajectory. So I'll give you a moment to try this. Someone brought up just in case somebody else was confused by the same thing. On the schedule, the links are at the top of the day 2 schedule. This is based on a notebook by Emmanuel that's posted in the resources, but that notebook is quite different, and yeah, it's not structured the same way. So yeah, make sure that you're working with the collab from here. So after you filled in the masking, you should be able to train this and produce some plots below. Could I see a show of hands of who's been able to produce that plot? A few, okay. Maybe I'll give some more time then. All right, in the interest of time, I'll move on. So this training loop here has the masking operation filled in. And if you were able to train this model, what you'll see as an output is a comparison of what happens when you are masking invalid forward actions versus and not doing so. And this is just a demonstration of how this can really help convergence when you're training these models with a fixed compute budget. I'm having a bit of trouble seeing from up here. Is everybody able to get these models training properly, or are there issues? Okay, I'm going to assume that means that everything is going well and I can move on. So what we can see here is that we're doing better. We're sampling now valid faces all of the time. We're still not sampling the correct proportion of happy faces. And our estimate of the partition function is better, but it's not correct. So what we're going to do now is to move to a better, loss function as presented by Kolya before, trajectory balance. So we're still using the same compute budget here, but we're now going to be implementing a loss that requires both a forward and a backward policy and an estimate of log z directly. So we'll implement our new model here, where essentially the first 6 elements of the output are going to be our forward policy. The last 6 elements of our output are going to be the backward policy. And it will also have a single parameter that is an estimate of log z. So oops. I go back here. So the next part of the exercise is to implement the trajectory balance loss, which is given to you here. That will accept log of PF, log of PB, the reward, and log Z in order to train the networks. Yes. Quick note, log PF, if you look at the training loop below, is accumulated. It's not a vector. So if you run into a weird bug due to shape, that might be why. Okay, I'm going to flip to the answer here, just in the interest of time. I'm guessing people are starting to get hungry, and we may not be able to finish the whole exercise. So what you can see here is that it's we're simply returning the sum of log P, log PF, the log of the reward that's passed to this function, as well as log PB. And then we're going to square this. The other thing that we need is backward masking for the backward policy. And this is this provided? Yes, it is provided. So this is 1 for any action that could have led to the current state. Otherwise, it should be 0. I won't ask you to do that here. But now I think first maybe the final major exercise is we'll complete this training loop that implements trajectory balance. So what are we doing here? We're looping through our episodes. We're going to collect our state, which is a list once more. Our model is going to produce PF of S and PB of S. And we're going to initialize our accumulated log PF and log PB. We're going to do a similar fixed length trajectory. We're going to be masking our forward actions. But here, since we're working on log space, the masking is happening a little bit differently. And the key elements that you need to implement are, where did I put them actually? So it looks like this is all given to you. So the idea here is that we're once again sampling the action for the forward trajectory. And we're going to calculate the log probability of that action and accumulate this. If we're at the end of the trajectory, we're going to calculate the reward. And then we have to do something similar for the backward trajectory. So we're going to use the model to calculate PB. And we're going to mask this as well with the masking function that we have derived before. And crucially, we'll be calculating the log probability of this backward action. I guess there is no fill in the blanks here. I think I made a mistake. But in any case, that's fine because we don't have too much time before lunch. But make sure that this trains and that you're able to see this curve below, which will show you both the loss and our estimate of the partition function throughout training. And we should see that it converges to the exactly correct value and that we're sampling not perfectly, but pretty close to the ideal proportion of happy and sad faces. Which is, this is supposed to be a demonstration of sort of the advantage of using this loss, even in an exceedingly simple example, we're able to see a difference in convergence. So please play around with this and feel free to ask questions if you're confused about any of the outstanding elements. I'll be happy to walk around. And then after you're finished, lunch is to your left. And thanks very much for your attention. Just so everyone knows, oh, is it cut off? I'll be uploading the answers to all of this later if you're interested in the same location.
Hello, everyone. Hello, everyone. If you have your belongings in that part of the room, please move it on the other room because we are closing this section for the afternoon, just because there will be a social event after the talk and the practical of the afternoon. So we need a bit of privacy to not disturb your session this afternoon. So if your belongings are there, please move it to the other side. Thank you. And enjoy the lunch.
SoundCloud? Yeah, SoundCloud.
Couldn't remember the name. SoundCloud.
Yeah.
I have more stuff on Bandcamp, but it's like a lot of.
I know the feeling. Yeah. I've got so much of that.
Afternoon.
I have so much of that.
But
But it's not online though.
This one's a little bit more curated. So how do I find my own thing?
You send me on Slack or something. I'll send you something back.
What's your name?
I'm Carl.
Carl.
Yeah,
I'm Joe.
Carl with a K.
Carl with a K. I used to work with a guy who called himself Carl with a K.
Yeah, it's usually us. If you're looking for me on Slack, that's going. And I think I'm.
Yeah, you're the guy with the little knob.
With the what?
The knob.
Yeah, that's me.
All right, done.
Awesome.
I'm looking forward to hearing.
Yeah, of course. Yeah, I'll send something. Whatever you're coming, someone send me something. Are there? Hey. Mike, aren't online? Okay, Mike one online? Okay, Mike two online. Mike one. Mike podium. And Mike three. Hey, this is Carl from Mila AV support. You can hear me, right?
Yeah, I can hear you.
Perfect. I can hear you too. Yeah, you can just go ahead and hit play. Okay.
Is it visible?
Yeah, that looks good. Could you just say a few words? I want to just make sure we can hear you in the room.
Yeah. Hello. Can you hear me?
Perfect. Yes, we hear you very well. Okay, so we'll soon be starting again. So you'll hear one of the organizers come to the stage, and then they will introduce you.
Yeah, sounds good.
Amazing. Thank you.
Thanks, Carl.
This one's gonna have more.
Okay. I just want to make sure I'm watching ready.
Check. Mic check. Mic check. And mic check.
And it's online.
Just waiting. Yeah. Oh, yes, good. Right. Welcome back, everyone. We have a few more presentations this afternoon before we all get to enjoy the social portion, if lunch wasn't social enough. So for our next presentation, our speaker unfortunately has to join remotely, and we hope that we'll be able to see him on the screen very soon. And the speaker is Moksh Jain, who is a PhD student at Mila, supervised by Joshua, and his research focuses on experimental design and probabilistic inference. Moksh, are you there?
Hi. Yeah, I'm here.
Good. Take it away.
Yeah. Thanks, Kolya. Yeah. Hi, everyone. I unfortunately can't see you, but thanks for joining us for this workshop. And today I'll be talking about conditioning and just generally conditional GFlowNets. So before I get started about conditional GFlowNets, I will do a recap of what we discussed in the morning, what was discussed by the other presenters in the morning. Just a short recap because I know everyone has had lunch and had, I hope, a lot of fun and interesting conversations, but just so that everyone is back on the same page again. And also, since I cannot see the audience, if you have any questions in the middle of the talk, please feel free to go to one of the mics and ask me the questions. Otherwise, I don't really have a lot of feedback here. Yeah, so let's get started. So let's do a quick recap of GFlowNets. So from Joshua's, Emmanuel's, and Kolya's talk, one thing which should be hopefully clear by now is that GFlowNets are amortized samplers, which are designed to exploit compositional structure to allow us to efficiently sample from high dimensional distributions. Now, when I'm talking about high dimensional distributions, I'm generally talking about things like graphs, sequences, or even continuous spaces, as we'll see later in the talk by Salim. The key aspect here is the fact that we learn the stochastic policy, which sequentially constructs the object that we're interested in. So if we want to generate a graph, we will generate the graph through a sequence of steps where each step consists of adding one particular building block to the graph. We want this policy to generate objects in a fashion where the probability of a particular object being generated is proportional to some non-negative reward function that we have. So this non-negative reward function R of x, if it is bounded, it can define a probability distribution, and we want to sample from that distribution. And that's what GFlowNets allow us to do efficiently. And that's what we learn the policy for. So let us go over some terminologies again. So the sort of generative process is represented as this directed acyclic graph. In the directed acyclic graph, the first thing we have is this special initial state S0. We have the terminal states denoted by a square in this particular animation. We have the intermediate states denoted as the circular intermediate states. The actions are basically the edges within this, are represented by edges in this directed acyclic graph. The trajectories are these arrows, which are just walks in this graph, or paths in this graph. A path which starts from the source state or S0 and terminates in a terminal state is a complete trajectory. A few more things that were also discussed. So I will be operating in the trajectory balance terminology. So no flows for now. We have this forward policy, which is just a conditional distribution. Given a state, you have over the children of the state, the probability of going to the children. Using the forward policy, if you start at S0, you can sample a trajectory by iteratively sampling from this forward policy until you reach a terminal state. You will get a trajectory. Similarly, we also have a backward policy which maintains a distribution over the parents of each state. And if we start from some terminal state, we can sample a backward trajectory all the way to the source state S0. Then we can also define these two terms, the first of which is the likelihood of the trajectory under the forward policy PF, which is essentially just a product of the probabilities of the intermediate transitions which compose the trajectory. And we can also define the likelihood of a trajectory under PB starting at a particular terminal state, PB tau of x, tau given x, as the product of these intermediate transitions and under the backward policy. And finally, we have the partition function, which is just the sum of which is just a sum of the rewards at the terminal states, or which is also the partition function of the distribution that we're trying to sample from. Now, the learning problem that we have in GFlowNets is we want to learn this forward sampling policy, which goes from the source state to the terminal state, such that the marginal likelihood of sampling a terminal state is proportional to the reward. So the marginal likelihood of sampling a terminal state is essentially a sum of the likelihoods of all the trajectories which lead to that particular state, and we want it to be proportional to the reward. Now, as Emmanuel and Kolya discussed, if we naively try to satisfy this objective, it's like a lot of an exponentially large number of constraints that you have to satisfy at each of the states in the state space. But we can have like some more higher level objectives, which sort of ensure that this constraint is satisfied on certain objects. So in the case of trajectory balance, it is the constraint satisfied over trajectories. In simple words, the trajectory balance constraint just tries to make the product of your partition function and your forward policy to be equal to the backward likelihood of the trajectory under the backward policy times the reward function, and you ensure this is true for all trajectories. And this sort of gives us this nice learning objective, the trajectory balance learning objective, which can allow us to learn the parameters to these policies, forward, backward policy, and the partition function through this nice squared error. And if this loss goes to zero everywhere, then we recover the desired policy, which samples which samples terminal states with the probability proportional to the rewards. So let's quickly go over like just the general procedure of training GFlowNets. And the reason why I bring this up again is because we will see how this differs for conditional GFlowNets when I talk about them a bit later. Spoilers, it's not a lot different. So to train a GFlowNet, we first start, as you might have experienced during the hands-on session just before lunch, we start with some reward function that we're interested in, and of course, which defines the space that we also want to sample from. And we can define an action space and a state space to get like the generative process for what we're trying to sample. Sorry. And this gives us our tag. And then we initialize our we initialize our partition functions, we initialize our forward and backward policies with some parameters theta. And then until some convergence criterion, which will be actually discussed a bit more tomorrow. But for now, you can assume, let's say, the fixed number of steps that we train for, fixed compute budget. We run the following. We will sample some trajectory from some exploratory policy, which Jared discussed a lot of options for earlier in the morning. So, for example, epsilon online policy. And then you just compute the loss for the trajectory. So in this case, this would be the trajectory balance loss. And then you update your parameters theta using gradient descent. So fairly straightforward. And as a result, you will get this desired policy, which samples proportional to the reward. I also want to highlight some key features that we get out of GFlowNets, again, as sort of foreshadowing things that we will also focus on for the conditional case. But the first thing is you get an estimate of the partition function for free. And this is sort of, this might seem somewhat straightforward in some ways, but it is also not. So like Yosha also highlighted earlier in the morning that typically when you have a sampler, you don't necessarily get these marginalization properties along with the sampler. So one example of that is just a partition function. And this partition function can be useful in a lot of applications, some of which I will discuss a bit later. Now there is this asterisk on free because technically you are training your policy and you are spending a lot of compute, so it's not necessarily free, but it's free in the sense that once you have a sampler, you get this estimate of the partition function along with it without any additional compute for that. The next thing is amortized or fast sampling. Again, something which Joshua and Emmanuel highlighted earlier in the morning is if you train once you have trained your policy, when you want to generate samples, you can just take sample a trajectory using TF, your forward policy, and you will get the samples from your target distribution. This is very powerful because typically in MCMC, you would have to run your chains if you want to get more and more samples. So this is quite important in scientific discovery applications. And final thing which Jared highlighted is off policy training. So the nice thing about the GFlowNet learning objectives is the trajectories that you train from don't have to come from the policy itself. They can come from any policy as long as the policy has full support. And we can compute this loss using any offline trajectory. So this gives us a lot of flexibility in terms of how we design our exploratory policy, which samples the trajectories for training, which can allow us to do very fancy exploration things. So, for example, the Thompson sampling approach that Jared mentioned earlier in the day. This is the brief recap of GFlowNets from the morning session. If there are any questions up until this point, hopefully not, but if there are, please feel free to ask them now before we start with conditional GFlowNets. Okay, I assume there are no questions because I didn't hear anything. But please stop me if there is anything. Yeah, so let's move on to conditional GFlowNets. So to start, let us consider this motivating example based on this very cool smiley face environment that we have seen throughout the 2 days of the workshop. Now, let's say we are sampling smiley faces or faces. They can be smiles or they can be frowns. And along with this faces, let me introduce another random variable, y, which is you can think of as a description of the faces. So for now, I've kept it simple. So this description is very basic. So it's evil smile, evil frown, innocent smile, or innocent frown. So it describes the features of the eyes and features of the mouth in the smiley face. And say I can also define this reward function. Yeah, this reward function, which basically computes how well the face and the description match with each other. So the reward function for the evil smile with the smiley face which has an evil smile is 2, and the reward for the smiley face which has the evil frown and the description evil frown is 2, and so on. So where the description and the face match, the reward is 2. Where there is some ambiguity, so for example, in this particular case, in this particular smiley face, it is hard to say whether it is evil or innocent, or it's both at the same time. So we give it a reward of 1. And where it does not match, let's say the reward is 0. Now, let's say I want to sample smiley faces for each of these expressions y, or sorry, each of the descriptions of the expressions y. So what the most naive way I would go about this is I have like 4 choices for y. So I will have 1 GFlowNet for each choice of y. So simply I train the reward function. I fix the expression to be evil smile, and I just train a GFlowNet for that particular reward function. Then I fix the reward function with an innocent smile, and then I train the GFlowNet with that reward function, and so on. Now, a lot of you might have already seen what is coming, but it is not very efficient. In this particular case, where we have only 4, you can still sort of do that. It's fine, it's feasible. But if you consider y to be a bit more high dimensional, so instead of just being 2 words from this select vocabulary, it can be just natural language. And in that case, it is not feasible to have 1 single GFlowNet for each of these values of y's. Another important thing to notice here is the reward function, which I showed earlier. For in both the cases with the evil smile and the innocent smile, this particular face has the reward of 1. So there is some information between both of these descriptions, which is common, which results in some common features in the space of the faces. So here it is very easy to observe, which is this smile, the word smile, it appears in both of them. So what this tells us is there is some shared structure which we can try to leverage in order to make this more efficient and not train like as many GFlowNets as the number of this additional variable y that we have. And this leads us to the idea of conditioning. So instead of trying to learn these y separate policies for each of the conditioning variable, each of the values of y, we can actually learn a single conditional policy which conditions on the value of y. And essentially what this means is we would share the parameters between each of these policies trained with an individual y. So essentially, let's say if we trained from the previous slide, if we trained the GFlowNet on each of these reward functions, we would get, these four different policies. What we instead could do with conditioning is just have a single policy which conditions on this on this description y, and what this amounts to is just sharing parameters between all of these policies. And there are several reasons why you want to do that. The first reason is it allows us to model the shared structure in these y's. So the shared structure could be things like the word smile being common, but more generally, it could be some more abstract structure. So if you have natural language, in natural language, you can have a lot of rich structure. If you have something like images, even if you're conditioning on images, there is a lot of structure to generalize from in images. So it essentially what it does is it allows us to generalize to unseen y, which is an important and very powerful concept. So even if we see, let's say, only a very small fraction of possible natural language descriptions, we might be able to generalize to some unseen natural language descriptions, assuming that we have like enough diversity in the data or in the examples of y that we have seen. So just as an analogous example, if you think about stable diffusion or DALI style models, they are trained on they aren't trained on like all possible English text and the corresponding images, but you see a small fraction and you're able to generalize this conditional model to some unseen natural language descriptions of like an astronaut on a horse on the moon, that sort of thing. So how do we actually operationalize this in the context of GFlowNets? That's where conditional GFlowNets comes in. So conditional GFlowNets in general, they're essentially just, instead of having a single DAG, we model a family of DAGs. But the special thing about this family is that it can be indexed using this variable y that we introduced earlier. So what I mean by this is, for example, if your y can take 4 different values, you can have you will have 4 different DAGs, but which DAG you end up in is essentially selected by the value of y that you have. And what this amounts to, in a sense, is just having this conditioning variable as an additional input to all your learning objects. So your flows, your policies, and even your partition function. So conditional GFlowNets, in very simple terms, are just have this additional input y at each state to all your flows. You have your conditional forward policies, conditional backward policies, and your conditional partition function. And to wrap them all up, we also have our conditional loss functions. So you just take everything which was discussed in the morning and you just add this additional conditioning variable. And that's basically it. So what this ends up doing is instead of modeling this any single DAG, your GFlowNet, which actually models the generative process, which defines the family of DAGs for all the values of y. And if you are clever about how you select the y's that you train for, I will get to this a bit later, you can even generalize to unseen y's. And this can be useful in a lot of different applications, some of which will be discussed tomorrow, and some of which I will allude to a bit in later in the slides. Yeah, so before I move on to like how we actually train conditional GFlowNets and what are like some examples of how to parameterize conditional GFlowNets, are there any questions based on things that I have discussed so far? Okay. I assume there are no questions, but again, please feel free to interrupt me if something is not clear. So let's see how do we train conditional GFlowNet. So here I'll try to contrast it with the procedure that we saw earlier in the presentation. And the things which are different from the previous example will be highlighted in red. So to train a conditional GFlowNet, you again start with the reward function, but you also start with this additional thing P of y, which is just some distribution which from which you sample this conditioning variable y. So this can just be like a uniform distribution over some data set of y's that you have, or it can be something more fancy depending on your application. And some of the examples I will discuss in a bit. But assume that you have some distribution P of y. You then define your state space and action space for generating x. You initialize your partition functions, forward policy, backward policy. But this time, all of them are the conditional version. So you have your conditional partition function, conditional forward policy, conditional backward policy, and so on. And then until convergence, you follow the similar recipe. So first you sample this conditioning variable from the distribution that you are given, or you assume. Then you sample a trajectory using your exploratory policy, but the exploratory policy again here is a conditional exploratory policy. And then you compute your conditional loss again, which is just a small, essentially just the trajectory balance loss, but with all the conditional components. I also noticed there is a small typo here. This should be PB. But yeah, and then you update your parameters theta with gradient descent. And at the end, you will get your conditional policy. So like I said earlier, it doesn't differ that much by that much from just training a standard GFlowNet, which you all did in the hands-on session as well. The only difference comes in here, the part where you have to sample. You just have this additional step of sampling your Y, and you just change all your learning objects into conditional learning objects. But apart from that, the procedure remains the same. Now, there are some other things which need to be accounted for when you are doing this. So the first obvious question is, how do we actually parameterize this conditional policy? So one thing which I mentioned was you can assume that this is an additional input along with your state. But how do we actually operationalize this? So there are a lot of ways of doing this, and there is no single best way of doing it. But I will discuss some choices which could be possible depending on the application. So the first one is to modulate the activations in your policy based on the conditioning variable. So what this basically means is, let's say you have your conditioning variable y. Okay, sorry, there was some issue here. So assume you have this conditioning variable. Okay, this seems to be happening again and again. Sorry, so you have a conditioning variable y, and you have some embedding for this conditioning variable y that you obtain from some encoder. What you can do is, for your policy, for some intermediate layers in your policy, you can change the activations or do an affine transform on the activations, which is defined using the embeddings of your conditioning variable. So this is actually something which is quite common in the diffusion model literature. This is how people define the time dependency in diffusion models. But the idea here is also similar. It's just an affine transform which is dependent on the conditioning value of the conditioning variable. Another option is simply appended to the input, like I mentioned earlier. So this is very natural in the case of natural language. So for example, if the conditioning variable here is a question, so what is 3 plus 4? And you are trying to generate the answer to this question, spoilers, which is something we are going to discuss tomorrow as well. But for now, let's assume that this is a question, what is 3 plus 4? And you want to generate the answer to this. So you can generate it like if you want to condition on this particular piece of text, you can just append it at the beginning of your inputs, all the inputs to your policy, and that will achieve the desired effect. Another option is to append it in representation space. So we assume you have an encoder for your conditioning variable, and you have an encoder for your states, and you just take the latent representations which both the encoders produce, and you concatenate them, and that's another way to achieve this effect of achieve this conditioning. So these are three choices. Of course, there can be a lot of other ways to do this, but there is no single best way, and you might want to try out things which work best for your problem. There are also other things in terms of how we actually instantiate the conditional GFlowNet. So for instance, you might want to share parameters between PF and PB and Z, which are responsible for doing the encoding. So for example, the encoder can be shared across all like PF, PB, and Z, or some parameters can be shared between PF and PB, and so on. So there is a lot of flexibility in terms of how you parameterize this. And this flexibility, again, also comes at a cost that you have a lot of things to try out. But generally, weight sharing does not necessarily hurt performance, as long as there is like some reasonable number of parameters which are set independent for each of the objects. And the final thing is this P of Y, which I mentioned earlier. What this allows is it allows us to define some preferences if we might have any on the Y's or the conditioning variables, and even things like specifying curricula. So you can start from simple examples of Y and then slowly go on to difficult examples of Y. And one specific case of this is something called temperature conditioning, which I'll get to in the next slide, which is also one of the questions on GeoLib. But before that, let's look at some other interesting instantiations of this conditional GFlowNet framework. So the first one is this preference conditioned multi-objective optimization. So what exactly is this set of words saying? This is the multi-objective optimization problem, which essentially means instead of having one reward function, say you have multiple different reward functions. So for example, in the case of drug discovery, you can have how good is a particular drug, but your other objective might be how toxic is it to humans. And ideally, you would like to minimize the toxicity to humans and while being very effective against the drug, against the target. But the problem here is both of these objectives might not be independent of each other. So making a drug more and more potent to a virus might make it more and more harmful to humans as well. So there is this trade-off that you have to strike. And essentially, this is called the Pareto front in multi-objective optimization, where you cannot improve one objective anymore without hurting the other. And sorry. So in this case, one strategy to do multi-objective optimization is this thing called preference conditioning, where essentially we assign some preference to each of the objectives, and depending on the value of the preferences, we focus on that objective. So, for example, in this point to the top left has very low weight on objective 1 and very high weight on objective 2, and the point on the bottom right is very high weight on objective 1, low weight on objective 2, and so on. So in this case, if we want to learn a policy which can solve these problems, what we would do is we would condition on the preferences assigned to the objective. So we want a GFlowNet which can condition on the preference and generate candidates which follow those preferences. And the reward is, again, also defined given this preference vector, which is just a weighted sum in this particular case. Another example of where conditional GFlowNets can be instantiated is that of parsing. In parsing, we are given, let's say, a particular sentence, and we want to infer the parse tree. If we want to infer a parse tree under some grammar that we know. Now, they can, in general, in language, you can have multiple ways in which you can parse a particular sentence. But here is one particular example. So in this case, you would condition on the sentence that you start with, and condition on this sentence you would like to build this tree bottom up in this particular example. So we would condition on the cat string T, and then the tree which is being built in these panels is the state space that we're operating in. So here we condition on the input sentence, and the reward again is in this case we are trying to infer the posterior over trees. So the reward here is defined also in terms of X. I didn't go into a lot of details on both of these applications, but these are part of papers which are on the website. So feel free to go there. But the point here is to highlight how conditioning can actually be instantiated and in a particular problem. Now, the final, more interesting case is that of temperature conditioning. So earlier in the day, Jared talked about how important it is to, and even Emmanuel talked about how important it is to have some temperature on your reward when you use it for your GFlowNet. And temperature condition in the ideal temperature conditioning is what if you actually condition on this temperature. So what this does is if you condition on the temperature and let's say you the conditional reward here is just the reward at that particular temperature. What this allows you to do is you can actually have some sort of annealing procedure. So you can start with very high values of the temperature, which will give you more exploratory behavior, and slowly reduce the temperature. And reducing the temperature can make your reward more and more peaky. And at the end, you can get like very greedy samples from the modes of the distribution. And because the model is conditioned on the temperature, you can, once your training is complete, let's say you have seen enough number of temperatures, you can actually get samples from any temperature that you want. And this gives you a lot of flexibility in terms of being more greedy, in terms of being more exploratory, and so on. So this is also another interesting instantiation of conditioning, which can be applicable in basically any GFlowNet application. And finally, I wanted to discuss intractable sums. This is again something which Joshua alluded to in his presentation earlier in the day. But one sort of nice feature about GFlowNets is being implicitly computing these intractable sums, these marginals. So in conditional GFlowNets, we get for free an estimate of this conditional partition function. And this conditional partition function actually encodes sum. The sum, which basically a sum of this reward function, which is defined over two variables, and we sum out one of these variables. And we get this intractable sum. And this is actually a very important quantity in a lot of scientific problems. So one example which I'll discuss a couple of examples, but one of them is path integrals and quantum mechanics. So in the path integral formulation of quantum mechanics, you have, let's say you want to study the probability amplitude of a particle going from point A to point B. Each of these trajectories can be assigned some, like all the trajectories going from A to B can be assigned some weights, which I denote here by R. If you consider like the sum over all of these trajectories, it corresponds to the probability amplitude of a particle actually going from point A to point B. And this is a very important thing which people study in quantum mechanics, which is an example of these intractable sums. Another example, sort of closer to home to machine learning, is latent variable models. So if you have a posterior distribution over some latent variable, the conditional partition function actually represents the marginal likelihood of the data in this particular case, which is in general an intractable quantity, but can be useful as a diagnostic tool or for various applications as well. So the idea here is that through conditioning, GFlowNets can sort of be even more flexible and sort of be applied to a variety of different problems and do more interesting things. So that's basically it for my presentation. If there are any questions, I'm happy to answer.
Would anyone with questions please come up to the microphones?
Hi, Mox. Can you hear me?
Yeah, I can hear you.
All right. My question is, I understand it's not exactly the same thing, but how would you say that prepending the conditioning variable to the state space, to your environment, as maybe the first action that your GFlowNet can take, how does that relate to the conditioning scheme that you described? One difference I could see is that, for example, PB wouldn't have access to it from the beginning, or maybe it would be sampled last. It would be fine. Like, is it the same thing? Do you see any difference there?
Sorry. So do you mean that what is the difference when we like if we are prepending it to our state space? Like how is it different from assuming that
Yeah,
is the
like
first action?
basically making it an action.
Yeah,
like something that the GFlowNet can choose on its own instead of having an external PY that you define yourself.
Yeah, so the difference here is like as you already alluded to, it's the fact that the backward policy, for example, does not have access to if it is an action, that the backward policy does not have access to this initial action, and it is not available at all states. What we want is to be it to be available at each state as like an even when we are sampling from the backward policy, or even if we are computing the backward policy. So if you assume it is an action, then it is not necessary. Like you can sort of make your MDP in a way that it is a condition, like it achieves the same effect. So yeah, it is possible to like just change your MDP so that assuming that it is an action in your MDP. So like if you structure your MDP appropriately, then it becomes a conditioning variable. But it's easier to think of it as just like an additional input present at all states, in terms of like actually like instantiating it.
All right, thank you.
Hi, Mox. Do you hear me?
Yeah.
Yeah, thanks for the talk. So I was wondering, is it always better to condition, or would there be cases where like having separate GFlowNets is like a better solution than conditioning?
That's a good question. I don't have a clear answer to this. I mean, if you have like it's just, for example, two things that you want to do and if the two things don't share any structure at all, then there is no point in conditioning. Like if the conditioning variable takes two values and those two values have nothing in common, conditioning doesn't buy you anything. And in that case, you can probably just train two separate GFlowNets. But it's so it's hard to say in general, but for example, like if there is clearly no structure which is shared between this conditioning, different values of the conditioning variable, then you probably might not want to condition. Maybe Kolya has something to add to that.
Oh, way to put me on the spot. I have one thing to add to the excellent answer, which is that there may be cases where you want to pre-train your model as a conditional one, and then fine-tune it specifically for the values of the conditioning variables that you're interested in. The pre-training can help you adapt very fast.
Okay, thanks.
So it seems like there are no more questions. Yeah. Right. Thank you very much, Mox.
Thank you.
Next, I'd like to introduce Lena Nehal-Ezin, who is the PhD student at UDM and Mila, supervised by Joshua. Her research interests are at the intersection of AI and drug discovery, with a particular interest in applications to curing cancer. And she will tell us about training GFlowNets for maximum likelihood.
Hi, everyone. So in this presentation, we're going to explore some links between GFlowNets and maximum likelihood estimation. So until now, we've always talked about GFlowNets as this framework where we have a reward in the end that we can train with. But how about if we don't have this reward and we only have a data set that we can train with? Yeah, so before starting, I want to acknowledge Shu, Kolya, and Dinkhoy, who were also working on this. So Shu was supervising me when I was working on this direction, and it's Kolya and Dinkhoy who came up with this idea and wrote a paper about it. So you can check this very nice paper, which makes links between GFlowNet and other generative models. All right, so for the motivation, so we've seen that GFlowNet can sample given a reward function. So this is an example of a negated reward function for terminal states in R to the power of 2. But how about if we don't have this reward signal? How about if we only have some samples from this reward distribution? And you can see these little colored dots here. And so we have access only to this data set here. Another way to look at it is in this little drawing. So in the left side, it's the setting that we are used to. We have a GFlowNet, we have a reward function that we can query for any data point. And this can be in a setting where the reward is very cheap to compute. There is then this middle ground where you have the reward function, but only for a finite number of data points. So this can be the case, for example, if you have molecules and proteins, and the reward is a function of their potential energy, but this potential energy can be expensive to compute, especially if you have large proteins. And then here on the right-hand side, it's our setting that we're going to talk about today. So we only have data. And it can be, for example, a data set of text, of images, etc. Okay, so for the motivation of this GFlowNet MLE, it's very intuitive. We start with terminal states from our dataset that we sampled, and we know that these samples are good according to some underlying reward distribution. We sample a trajectory backwards, and then we want our GFlowNet to increase PF for this sample trajectory. So in more mathematical words, we want our GFlowNet to maximize the log likelihood of our observed data, but it's hard to optimize this thing directly. So what we do is we optimize a surrogate loss called elbow, which we've heard about yesterday morning. And so the idea of this elbow is exactly what is written here. We start with the terminal state X. We sample a trajectory backwards. And what we want to do then is to increase the forward PF for this trajectory tau. And so here it is. Now we have a loss to train our GFlowNet, and there is no need for any reward signal. So we introduce the scale trajectory balance loss, which depends on PF, PB, and your terminal state X. So this is the algorithm to train our GFlowNet MLE. We have a training data set, and we sample terminal states. We sample a backward trajectory from this terminal state, and then we compute the scale loss. And we simply backprob for PF and PB through this scale loss. So this algorithm works, and we can train the whole GFlowNet MLE just with this algorithm and train both PF and PB. But there is another way of doing it, and we'll see in the end that it's equivalent. But this way, I find it more intuitive. And the idea came from Kolya. So the GFlowNet losses all contain this reward signal. And this is problematic in our case. So how do we get rid of this reward signal? Well, we can use two trajectories instead of one. And these two trajectories need to end up in the same terminal state. And when we look at their TB loss, what we can do is combine these two TB losses in a way such that the reward is going to cancel. And we are left with this new loss that we call the consistency loss between two trajectories and the terminal state. And it's basically just the difference between the log of the fraction of PF divided by PB for the given trajectory. So another way to look at it is that from this elbow calculation, we can show that the log likelihood of our training data is maximized if and only if PF and PB are proportional given a terminal state. And that means basically that this quotient PF divided by PB does not depend on the trajectory that you take. It should always be equal to the marginal of this terminal state when our GFlowNet has converged. Yeah, so the idea is that instead of using this KL trajectory loss, we're going to update PB by using this new consistency loss. So you might be wondering, okay, but what does it mean intuitively, this consistency loss? And this is a very simplified example. So we have a simple GFlowNet with two trajectories, one that is black and one that is gray. And we have one terminal state with the reward equals to 1. And so PF and PB are going to be like at the beginning they are independent. They're not necessarily consistent with one another. And what can happen at the beginning of training is that, for example, the PF for the black trajectory is gonna have 75% of the weight, and of the gray trajectory is gonna have 25% of the weight. And you can see that this is not consistent with the drawing that is on the right, where PB for the black trajectory is only a quarter, and PB for the gray one is only 3 divided by 4. So we have that PF divided by PB is different in the two cases, and it intuitively doesn't make sense because we want these two things to be consistent with one another. And also another thing is that we can use this consistency loss. Also, we can see it as a regularization loss that we can use with other losses like the TB loss or yeah, any loss related to the trajectory. Okay, so now you might be wondering, does this how does this consistency loss relate to this scale trajectory loss for PV? Does it mathematically make sense? Is there a relationship? And it turns out that yes, if we name phi the parameters of the backwards probability, it turns out that the gradients of the consistency loss and the gradients of the KL loss are the same up to a constant. So this proves the correctness of optimizing PB with using this consistency loss. So what we can do this time is that we're gonna optimize the forward policy using the first loss that was introduced, which is just take the terminal state and make sure that you increase PF for these good trajectories. And then we can make sure that all of the trajectories that lead to the same terminal state are gonna be consistent by using this consistency loss. So we obtain this other algorithm. So we have our training data set again, and we sample a terminal state. We sample 2 different trajectories, tau and tau prime, that both end up in the same X. We compute the KL loss, update the parameters of the forward probability for this KL loss, and for the PB, we're going to use this consistency loss. And that's it. That's the whole algorithm. Okay, at this point, you might be wondering again, okay, but why do we need all of this? We already have other generative models, we have diffusion models, we have VAAEs. Why are we using GFlowNet? But is it really that different? And this is what Dinghuai shows in this paper, Unifying Generative Models with GFlowNet and Beyond. So it turns out that there is a very close link between all of these frameworks. So for example, for hierarchical variational autoencoders, which is this framework where you have hierarchical latent variables, this HVAE is exactly similar to training the GFlowNet, and you can define the trajectories of your GFlowNet as being this succession of the latent variables. The decoder is going to be the GFlowNet forward policy, and the encoder is the GFlowNet backward policy. And you train your HVAE using the KL trajectory balance loss for both the encoder and the decoder. So for both PF and PB, like the first algorithm that we saw. Okay, but how about for diffusion models? Well, diffusion models are a special kind of GFlowNets. So I don't know if the figure is visible, but in diffusion models, you have your initial image, and then you add some noise to it to obtain like a noisy sample in the end. And this is the forward diffusion. And this forward diffusion is exactly the same as the backward GFlowNet policy, where you have your terminal state and then you just deconstruct it. And the reverse diffusion is the same as the forward GFlowNet policy, where you have some noisy thing and then you want to sample a good sample. So it's like just opposite words, but they are referring to the same thing. So diffusion models have some specificities in that the intermediate and the terminal states have to be in the same space. Like, for example, in here, all of these states are images. Yeah, the backward probability is fixed, so it's a Gaussian, and we know like what is the amount of noise that we add at each step. And what we learn is the PF, and more specifically, like we parameterize again PF as a Gaussian, and what we learn is this mean mu. And again, you can find more details about all of this in this paper. Yeah, so that's it for the theory. And for the experiments, we ran some very simple experiments on different 2D toy datasets, where the datasets consist of these 2D coordinates. And we train our GFlowNet with the samples from this data. And in the end of training, we are going to sample some points and plot them. So this is what we see in this top row here. And yeah, sorry, this GFlowNet is trained with the second algorithm. So we use scale, trajectory, balance loss for PF, and we use the consistency loss for PB. And on the bottom, you can see samples that are from the true data distribution. And like the GFlowNet is doing a good job in general, except maybe here for the moons where it's not that perfect, but in general, it is able to fit the distribution. So that's it. Thank you. And I'm happy to answer any question.
Thank you, Lena. Oh. Thank you, Lena. So you focused a lot on the consistency loss, which is basically operating over the whole trajectories.
Mm-hmm.
Can we have something similar at the level of like some more local information like this? What I have in mind is going from trajectory balance to, for example, detailed balance.
Mm-hmm.
We have something like some kind of consistency losses that can do that as well.
So you mean, can we define consistency loss, but for like locally? Is that what you mean?
Yes.
I think it makes sense to me that it should be the same thing. I need to think about it a bit more. But I think it should also be valid locally, because you always want, like, given two trajectories that end up in the same state, it means that they have the same flow in the last state. So you still want PF divided by PB to be the same. But yeah, it's like there has to be an intersection at the beginning and in the end, and in the end.
Okay.
But yeah, that's just an intuition. I need to write the math to be sure about it.
Thank you.
But it's a good question.
So has there been experiments using consistency loss in outside of the maximum likelihood framework?
No, there hasn't, but there are plans to use it. Like we haven't thought about using it as a regularization objective until like 2 days ago when I was talking to some friends about it. So yeah.
So I have another question. You mentioned that with the maximum likelihood training of GFlowNets, we end up with special cases corresponding to existing approaches like hierarchical VAEs and things like this and diffusion models. Is there any advantage to like putting these methods under the GFlowNet framework? Does it bias something that we might not have thought about before we realized that these are special cases of GFlowNets?
Mm-hmm. That's a good question, and I don't know. Like maybe that's just an intuition, but for example, maybe you can relax these conditions of diffusion models where you constrain PF and PB to be Gaussians, and maybe you can learn more complicated distribution that can be more expressive and can help for the training.
So I know that in chemistry applications, they use diffusion models with extra objectives that they want. And they use some heuristic where during diffusion, they go in the direction of the gradient of the property that they want to maximize.
Oh,
So I wonder if this is a scenario where the GFlowNet perspective could be less of a hack.
so do you mean in chemistry we use the samples, but we use another signal?
Yes,
Okay.
exactly. So typically they would have both a training data of samples, but they also have some neural net
Mhm.
that computes properties that they want to have. So think
Oh.
of it like we have examples of good compounds for a particular task,
Mhm.
and we have a neural net that predicts toxicity. So we'd
Mhm.
like to have compounds that look like the good ones, but also are not toxic.
So is it a bit like having samples, but also some kind of reward function?
Yes.
Like both the
Yes,
two
exactly.
of them. Yeah. So you cannot train with the reward function for diffusion models, but for GFlowNet you can maybe use both. And that's going to be a powerful advantage. But yeah,
But nobody has tried that, as far as you know. I mean, in the GFlowNet community.
Sorry?
Nobody has tried that kind of thing, like combining a data set for which you. So it's not what we have tried is we have a data set and we have a reward function, and the data set is just a guide to make sure we get the right reward. But this is a case where you have a data set that gives you some information, and you got also some extra, like a separate objective. You've got also a reward function that tells you some things you'd like to achieve in addition to the implicit information in the data set. So it's an idea for a new project. Oh yeah.
All right, make a short comment.
Yeah.
By the way, thank you for the excellent talk. Actually, one thing we'll hear, there might be more questions, Elena. So one thing we'll hear about in the talk by Salem, which is coming up next, is continuous GFlowNets. And actually, this view of diffusion models as GFlowNets trained with maximum likelihood allows us to train diffusion models to match a reward function. And we have experiments in which we do pretty much exactly what you just asked about, where for instance, we've tried to train GFlowNet for maximum likelihood, like a diffusion model, and then, for instance, fine-tune it or use as an auxiliary objective a reward function. And I don't know about chemistry, but it's useful for inverse problems, for instance, where the prior is given by a pre-trained diffusion model, and we have an extra likelihood, which is the evidence that we want to multiply into it to get the posterior.
Great, thanks.
Sorry, I can't hear you.
Joshua was saying that it's like the data set is referring to something, but the reward is not like, it's not a reward function. It's like two different. Yeah, it's like two different objectives.
Yeah, two different objectives. As long as they don't contradict each other, that's possible. Yeah, right. Thanks for letting me insert this. I think now Tristan has a question.
It's just a comment on the same thing. It could also be, but it's a comment question, but like, is it not like the strength of GFlowNets here would be also hard constraints? Like when I think of the crystal GFlowNet work with Alex, it's like when you have those, for example, symmetry constraints or whatever other hard constraint that you have, it's the masking in the state space is actually something that's easier to do and implement and enforce with GFlowNet instead of having that in the losses of a systematic network that. So I think that's also one strength for the same setup. If you have hard constraints that you know from your domain, I think GFlowNets give you more control there.
So is it also possible with the MLE framework to train the GFlowNet with a fixed backward policy the same way that you would do with the diffusion model and bypassing completely the consistency loss?
You can fix the backward policy and find one forward policy that's going to work for this, and just maximize for the
KL.
The KL loss. Yes,
okay.
Yes, it's totally possible.
Okay, thank you.
So thank you.
So now we'll take a break until 3:30.
Sun. Hey everyone. Just want to make a quick announcement. Maybe like a week ago, we sent you a link through Eventbrite to kind of submit your ideas and get feedback. I think there was something like GFlowNet Clinic in the email title. So, we've had a few very interesting responses, but tomorrow we're going to have about an hour session. So if you can have some ideas that you want feedback on, either prepare them for tomorrow, the mics will be open, or go and fill in that form already, and we'll try to think of some good answers in advance. So thank you.
All right. Next, I'd like to introduce Salem Ahlou, who will talk about continuous GFlowNets in continuous state spaces. Salem is a PhD candidate, I think about 2 weeks away from being a PhD period, yes. At Mila, supervised by Joshua, and he, during his PhD, has worked on uncertainty estimation and on theory for GFlowNets. And currently he's interested in automatic curriculum learning and in using GFlowNets for reasoning. Salem, can you say something?
Yes, do you hear me fine and see my screen fine?
Good, and you can hear us. Good.
I do hear you. I don't see anyone, but I guess that's normal.
I think that's normal. All right. Okay. Thank you.
Great. Thank you for joining my presentation about continuous GFlowNets. This presentation is mainly following a paper that was published in ICML this year, which was joint work with Tristan, Pablo, Jinghuai, Alex, Sasha, Lena, Kolya, and Joshua. I hope I didn't forget anyone. I should have written that. I guess like the first question to ask is, why do we need continuous GFlowNets? And you have probably understood from the previous presentations today that GFlowNets have proven advantages, either theoretically or experimentally, compared to MCMC, compared to reinforcement learning, and to variational inference. So compared to any of these three domains, like GFlowNets have some advantages. For example, off-policy learning helps GFlowNets more than variational inference. We can sample proportion to rewards rather than maximizing a reward as in reinforcement learning, etc. And also, these proven advantages have been confirmed in many discrete domains, discrete scenarios. For example, in biological sequence design, where the goal is to construct molecules or biological sequences by concatenating small building blocks, such as small molecules or maybe small proteins in general. It has been confirmed in Bayesian structural learning, where the goal is to learn a graph or a DAG that describes the generative process of a given data set. And here the construction of such a DAG is done sequentially by the addition of edges, directed edges between different nodes. It has been confirmed in the robust scheduling problem, where the goal is to assign a set of operations to different compute nodes or threads, which is known to be an NP-hard problem, and the GFlowNets have been shown to be useful for that. And actually, it's probably still state of the art today. It has been used for discrete image modeling. This is a paper that was published a year or so ago, where and the image you see here is binarized MNIST, where we construct these images of numbers that are binary, so just ones and zeros, given like a set of images. And the way this is trained is with maximum likelihood training that has been presented by Lena in the last talk. And probably many, I mean, not probably, but like surely many other discrete scenarios in which GFlowNets have been proven to be advantageous. So with these 2 points, the fact that there are many advantages and the advantages have been proven in discrete domains, there is the question, I mean, the fact that there are many interesting sampling problems that do not exhibit this discrete-like structure. This is what drives us to create a theory for continuous GFlowNets. And these problems that do not exhibit a discrete-like structure, I'll cite a few of them. The first one being Bayesian structure learning with parameters. So if we go back to the Bayesian structure learning in the discrete case, where the goal was just to learn the graph, which is a discrete object because we just need to create edges, or to learn where to put edges between the nodes. Here we also want to learn the parameters, and the parameters are in such a Bayesian DAG, the parent of a node influences its children, and this influence is captured by a function that can be parameterized either as a linear function or by a neural network. And in addition to learning the edges that tell us which are the parents and which are the children, we also need to learn the parameters of these functions. Another interesting problem is learning molecular conformations. So in addition to learning the molecule structure, we also sometimes need to learn the angles between some of the edges, or maybe the bonds. That's maybe the more correct term in molecules. Given that these angles influence the energy of the molecule, some molecules with some angles are more stable, are more suited for a given task. And finally, a last task that comes to mind is image generation, colored image generation, where we are not limited to only ones and zeros, where we can choose what color we want for every pixel. And obviously, you can think of many other scenarios where the sampling problem does not exhibit the discrete DAG structure. So I believe with these 3 points, it's obvious that to ask the question of whether there is an equivalent of GFlowNets in the continuous domains, and whether these advantages transfer to the continuous domains. And before answering the question, I will give you a summary of the paper, of what we found while working on this. And the answer is yes. There are a few details to be aware of when training a GFlowNet in a continuous domain. And I'll start by reminding you of the 2 main losses that are used in the discrete settings, so the detailed balance and the trajectory balance. And for the detailed balance, I'm not writing the boundary conditions where we incorporate the reward, but that's something that should be added to the detailed balance, of course. And I just want you to see that here in the detailed balance and the trajectory balance, the policies we care about are parameterized by their probability mass functions. So the PMF here, it's the probability mass functions. The policy PF S prime given S is a probability mass function condition S. And sometimes we need state flows. So as Kolya mentioned, when we don't use the flow matching conditions, we need extra objects such as the state flow function and the backward policy, which is also a PMF. And for the trajectory balance, but also for the detailed balance, of course, we need the reward function. So for the continuous counterpart, we also have a detailed balance and trajectory balance losses. And the equations look very much like the discrete ones, except that now, for example, for the detailed balance, we do not deal with PMFs, probability mass functions, but we deal with PDFs, the probability density functions. So here, PF S prime is a probability density function of S prime condition S. Same thing, instead of a state flow function, we have a state flow density function, and I'll talk a little bit about the details later. And again, instead of the reward function, we talk about a reward density function. But besides these three differences, also, of course, for PB, the equations look pretty much the same. So we can maybe like stop the talk here and say that, yeah, of course, you can train a GFlowNet, just use PGFs instead of PMFs, and use the same losses with in the log domain to make it more stable. But I'll delve a little bit into the details now. So the first question which is important to answer is, in the discrete domain, the structure is well described by a DAG. We have parents, we have children. We know that in order to go from one state to another, we have to go through this DAG. This DAG captures the structure we want. But in continuous domains, it's a little bit unclear how to talk about or how to generalize the concept of children or how to generalize the concept of parents. It might be a little bit weird to talk about continuum of children or continuum of parents. But still, we need a way to describe something that looks like a DAG structure in a more general space. And so we need some mathematical tools to replace this DAG that we use in the discrete domain. And we need this mathematical tool to satisfy a few desiderata. The first one being, we want to be able to describe a continuum of children and parents, as I mentioned. And we want this continuum to be of arbitrary dimension, meaning that you can have one state that has a unidimensional set of children where, like the children lie in a line, or maybe a bidimensional set of children where the children lie in a square or a disk or something like that. And the second thing that we would like is the ability to mix between both continuous and discrete components, because there is no reason to restrict ourselves to the continuous setting only. And one example or corollary of this thing that we want is so we want the child set of a state S. It can be the union, for example, of a continuous subset of the state space and the exit state. And this exit state that we denote SF sometimes. Basically, if we are able to describe a child set that is this union of continuous and this singleton called SF, this literally means that we can terminate trajectories early. So we do not require the trajectories to have the same length. And just because we want trajectories to not have the same length, we need to be able to describe child sets that include this singleton SF. That we'll refer to from now on by the exit or the terminate state. And I'll just show you a few sketches of examples of environments that satisfy these desiderata. Here in the bottom left corner, we consider an environment which is a square. So our points lie within this filled square. It can be anything within this square. And we can consider the starting point to be the bottom left corner. And then we can move anywhere within this quarter disk that is shaded here in gray. So by quarter disk, it means that the set of children of S0, the start state, is a continuous component of the state space, and it is bidimensional because, again, we can move anywhere in the disk and not just the circle. But after this first step, we can constrain the following steps to be within a quarter circle. And I believe that you see it a little bit here, like we have, for example, if you are in this point here, then the next state can lie within this quarter circle here that is centered around the current state. And of course, it has to lie within the square. And so this sketch here shows two trajectories of different lengths. For example, here, after 3 steps, it was decided to, the policy decided to terminate. So it went to the exit state, whereas here it required a few more steps. Another example that we would like to be able to solve with our theory is the one where the number of steps is fixed. We start from an abstract state S0 that does not represent any physical property whatsoever. But then we will make, for example, 100 steps, and at each step we will sample from a fixed distribution. I mean, not fixed distribution, of course, like we need to learn the parameters of the distribution, but like from a distribution of a fixed family. For example, we can set the family to be Gaussians, and if our space is R2, like the Euclidean space, we can just have, for example, Gaussians with fixed mean and learned variance, or Gaussians with learned mean and fixed variance, or things like that. And after each step, we will sample from a Gaussian until we reach the 100th step. Then we have a state at which we are obliged to terminate. And as a last example, before delving a little bit into the theory, which I promise won't be very mathematical, is the image generation problem, where we start from an empty canvas, that's S0, then we have to choose which positions, pixels to fill in, and which color to use for those pixels. For example, here the set of children of S0 is a continuum, because sure, there is a finite number of positions, just 9, but there is an infinite number, or like a continuum of values that each pixel can take. And interestingly, some states can have multiple parents. For example, the state here that has red and blue in these positions have 2 parents here, because here the forward policy has both a continuous and discrete part. The discrete part is the choice of the location, the pixel, and the continuous part is the choice of the color. But the backward policy only has a discrete component. Here, like if we want to choose what parent S2 has, we just need to remove 1 pixel. So, and the number of pixels is finite. So this is one typical application of continuous GFlowNets. So I mentioned before that we need a mathematical tool that allows us to describe a continuum of children of arbitrary dimensions, and that allows us to mix between both continuous and discrete parts. And the appropriate mathematical tool we came up with is transition kernels. And very broadly, transition kernels can be seen as a generalization of the concept of measures. I won't go much into the details, and I invite you to read the paper if you want like the mathematical details, but these transistor kernels are basically functions that take as input a state S and a subset of the space, and this subset of the space, we call it B belonging to this set sigma here. And basically it tells you whether the set B is accessible from S. That's what you need to remember from this. So if kappa SB is positive, it just means that part of the set B is accessible from S. It means it contains some of the children of S. If it is 0, it means that B is not accessible from S. And of course, there are a few caveats with open, closed sets, but again, I won't spend much time on it. And going back to the previous examples, where we had the quarter disk and the quarter circle, we can consider these 2 points here. For S0, for example, kappa S0B is 0 if B is outside this quarter disk. And so that means that the support of kappa S0 is the quarter disk. And if you are not at S0, if you are at another point, then the support of kappa S is the quarter disk. For example, if you are at this point, the support is the corresponding quarter circle and not quarter disk. Of course, we have to add to add the singleton SF to mention that we can exit at any point. For the other example, where we start from an abstract state S0 and take a fixed number of steps, our state space is this abstract S0 union. So we have to add a timestamp to our states, which are just normal vectors. So the support of kappa S0 is basically the Euclidean space, but we need the timestamp to be 1. So we need states of the form S1. And if you are at a state ST, then the support is the states of the form ST+1. So with this in mind, like with this transistor kernel as the basis of our theory, the generalization of the DAG that we came up with, we called it measurable pointed graph. I promise I will not read this slide, but this is just for reference, and maybe like if you want to ask questions later. But it requires the specification of the state space and these kernels that tell us what are the children and what are the parents of every state. I will, however, mention these two last points here, which are two important points that you need to be wary of if you want to train a continuous GFlowNet. The first one is you need to make sure that your trajectory lengths are bounded, meaning that you do not want some of your trajectories to have an infinite number of steps. So that's something that you need to enforce in the design of the environment. And of course, there is a mathematical formula for that. And you also need to ensure that all states can be reached from S0, meaning that there is no part of the state space that is unreachable. Again, of course, there is a mathematical formula for that. I will summarize now the key differences and similarities between discrete and continuous GFlowNets. So in the discrete, we talk about the children and parents of a state S, whereas in the generalized GFlowNets, we need to talk about supports of measures, kappa and kappa B. We don't need to spend a lot of time on measures. It's just like the mathematical tool that is required for the theory, but I just want to highlight that there is an equivalence for the notion of children and parents. And instead of the state flow function, we need to talk about a flow measure now. And this measure can have a density, U. Instead of the forward policy, we need to talk about a forward kernel that has, of course, a density that we write by small pf. Instead of the backward policy, we have a backward kernel that again has a density. And instead of the reward function, we have a reward measure that has a density. Again, these are just mathematical details, but at the end of the day, we have losses that look exactly like, at least for reward matching, detailed balance, and trajectory balance, these losses look exactly like their discrete counterparts. And let's just focus for a second on the detailed balance one, where instead of the state flow function f, we have the state flow density u, so that's us. So theta is just the set of parameters. And instead of the probability mass function pf, we have the probability density function small pf, and same thing here in the denominator. And of course, we have pretty much the same thing for the trajectory balance loss that is applied to trajectories of length n. We don't need to spend time on flow matching, but there is some small differences with the discrete flow matching, and that's because of the choice that we made in the design of the structured space. But all in all, the training strategy is exactly the same as the one that you have learned for the discrete GFlowNets. You sample your trajectories either according to the current forward policy or kernel, or you can add some noise to it if you want to go off policy, if you want to explore the state space more efficiently. And once you have that trajectory, you either decompose it into transitions if you want to use the detailed balance, or consider the trajectory as a whole if you want to use trajectory balance. You need to evaluate these terms that are inside the loss, and in order to do that, you just need to make a few forward passes in your neural networks. You because basically this density U, the flow density U, or the forward kernel density PF, for backward density PB, they're all parameterized by neural networks that take as input a certain state. And once you do this forward passes, you get what's inside the square here, and you can just evaluate the loss, gradient step, update the parameters, repeat until you're satisfied with the results. So that's about it for the theory, and I'll spend the next 5 to 8 minutes talking about a few experimental results we have, and then we'll have some time for questions. So as a validation of this theory, so this is not like a really interesting use case of GFlowNets, but more, it should be seen as a validation of the theory. We consider a continuous version of the hypergrid toy task. So this hypergrid toy task has been used in many GFlowNet papers, including like the original one by Manuel. So the state space is this square, 0, 1 squared. And the reward function is sparse, that has 4 modes, and the modes are represented by these 4 small squares in yellow. And the transitions follow the example that I showed a few slides ago, that actually I will show again. They follow this rule here. We start from S0, we need to move within the quarter circle of a given radius that we call rho, for the first step, and after the first step we can either terminate or move within the quarter circle again of the fixed radius. So now I'll go back to the other slide, but basically once we have this strategy that describes our measurable point of the graph, basically it tells us what are the children, what are the parents of every state. So this design, basically it makes the environment satisfy the constraints that we had before. So all the equations, especially the last 2 ones that I said, that trajectory length needs to be bounded and all states reachable by S0. So this is satisfied, and you can convince yourself with it, I suppose, pretty easily. So in the second image, so this one here, we see samples from a GFlowNet trained with trajectory balance. Actually, it's not really samples, so we train a GFlowNet, we get samples from that, and then we fit a kernel density estimator, and we get this nice contour plot. And the choice of the policy we made is, that's why we have circles or disks instead of squares. It was like hard to, I mean, we can probably prove that it's impossible to reach square densities like this, like with step function, with the choice of densities we made. So there is an important caveat of continuous GFlowNets that I would like to highlight here. So in discrete GFlowNets, and this is actually for the next 3 figures that I will explain. So for the discrete GFlowNets, the policies, whether it's forward or backward, they are parameterized with logits. So the neural networks that take as input a state S, they output logits that represent a categorical distribution, because we have a finite set of children and we just need logits for that. But with continuous GFlowNets, we have an extra degree of freedom, because we need to choose the family of distributions we want. For example, we can choose our policy to be Gaussian, and for that we need our neural network to output the mean and the variances, or maybe just the mean, as a function of the current state. Here for this example, we chose a mixture of beta distributions. And why it's beta distributions? So beta distributions are continuous distributions over compact domains, so it's bounded, as opposed to Gaussians, which are unbounded. So that's why we chose betas, and we chose it to be like a mixture of betas in order to describe a richer family of distributions. So if you use this mixture of beta distributions, we need to output the mixture parameters that, like the parameters that tell you I guess you know what mixture of distribution is. I don't need to explain that. And we need to output the concentration parameters of the betas. So this poses something to be, it leads to something to be extra careful about. Basically, we need to make sure that the family of distributions we are dealing with can satisfy the detailed balance or the trajectory balance conditions. Because if we choose like a poor family, maybe we can never reach a zero loss, because as in like the detailed balance or trajectory balance can never be satisfied. So this is what the next three figures show. So the first one, so this one here, what does it show? We consider a uniform backward policy. So by that, I mean that every state has a continuum of parents that belong to a quarter circle that is in the bottom left of that state. So of course, the radius rho. So we start with this backward policy, and we start with samples from the reward distribution. Like we directly sample from the true reward, like because it's a toy task, we have access to the true reward. And with these samples, we take backward steps using the backward policy until we reach S1. S1 meaning the state that comes right after S0. So that's why we get a landscape or a support that is within this quarter disk. So this is rho, that is the radius. And basically, we bring back the samples to S1 and we fit a kernel density estimator and we get this distribution here. So this is the distribution that this is what the forward policy at S0 should lead to. And, like there is a huge mass here on the left edge, on the bottom edge, there is some mass here in the middle, and it's pretty hard to match that on one step using a mixture of betas. Whereas if we consider a learned backward policy, then if we do the same process of starting with samples from the reward and bringing them back to S1, then we get this nice plot here where the mass is more regular, and it is easier to match that with a forward policy that is a mixture of betas. And this is represented by the fifth figure here. And what this means, basically, is that whether it's detailed balance or trajectory balance, these conditions are satisfied better if the backward policy is learned. Meaning, by satisfied better, it means that the loss reaches something that is closer to zero. And this is again shown by the learning curves here in the bottom. Maybe you can just focus on trajectory balance in blue for radius equals to 0.25, where we see that if we fix PB to be uniform, then we plateau to something that's around 3 times 10 to the minus 3. Whereas if we learn PB as well, then we are allowing PF to match this learned PB more easily. So the detailed balance or the trajectory balance condition is satisfied more easily, and we are able to reach a lower value for the loss. And of course, this is also apparent in detailed balance and also apparent if we change the radius. I'll stop talking about this example now. I guess I spent more time than expected, but I'll be happy to ask questions, to answer questions about it later on. And I'll quickly talk about this task of learning molecular conformations. So we are given a certain molecule where the atoms are fixed, but we have 2 degrees of freedom, which are these 2 angles, psi and phi, or phi. And basically, these 2 angles, they influence the energy of the molecule. So the molecule is more stable given some configuration of these 2 angles. So one particularity of this task, and this is why I'm talking about it, is that the state space has an interesting topology, because these angles, basically, let's call they live within the 0 to pi, and 2 pi is the same thing as 0 in if we talk about angles. so if we talk about just one angle, we're talking about a circle, because 2 pi is the same thing as 0. And if you talk about two angles, we talk about a circle that is horizontal and a circle that is vertical to that. And we are given a torus, and torus, something that looks like a donut. So our state space is a torus. It's not the normal Euclidean space. And you can think of it this way. Basically, this space that is represented by a square, you should wrap it, wrap like WRAP in your head, where the right edge is the same thing as the left edge, and the top edge is the same thing as the bottom edge. So this is a projection of a torus in the square. So this left figure here, we have the energy landscape from which the reward density is derived. This is the true energy landscape that tells you for a given value of psi and phi, what is the corresponding energy. And here in the right figure, this is the energy landscape that is obtained by fitting kernel density estimator on samples from a trained GFlowNet. And we can see that we can match the true energy landscape pretty accurately. But again, like the point of this slide is just to mention that we are able to solve tasks that have an interesting topology that is not just Euclidean. And finally, as a last experiment, I'd like to mention this one about posteriors over graphs and parameters. So it's Bayesian structural linear width parameters that I mentioned in the first slide. I'll show it again actually before going to the details. It's the task here where the goal is to start from an empty graph that represents the nodes, and then the goal is to add the edges sequentially. And once we are satisfied with the structure, then we have to learn the parameters that are associated to each one of those edges. And long story short is that we compared GFlowNet to before comparing, what this task is you are given a data set of, let's say, 3 variables. So it's just a set of points in 3 dimensions. And the goal is to construct the graph between 3 variables that tell you, which are the parents, which are basically the graph that generated this data. And we did this with 3, 4, or 5 variables. And back then, and I guess still now, back then, the state-of-the-art algorithms were BCDNet and DIPS. They took this data set and they output a posterior over graphs. And the numbers that you see here are basically the Jensen-Shannon divergence between the learned posterior and the true posterior. And long story short, like the lower it is, the better. And what we found is that with the GFlowNets, we get significant improvements. So we can surely say that GFlowNets are currently state-of-the-art algorithms. I don't know if something has come since then. This is like February 2023, but it's either state-of-the-art or almost state-of-the-art today. So this concludes my talk. I just want to shamelessly advertise this Torch GFN library that now supports continuous environments. And Joseph will probably talk a little bit about that in the next presentation. And, these are the references that I used, either the papers or the figures that I copied. And thank you for your attention, and I'd be happy to hear your questions now.
Anyone with questions is welcome to come up to the microphones.
Yeah. Thank you for the nice talk. Now, I have a question about which policies we should use in practice. So in my understanding, that in diffusion models, people, for example, for images, people use Gaussian policies. And for molecular conformation, I think people use graph neural networks or something. But I'm curious, in GFlowNet's case, let's say I want to sample from just EXP, reward function, which policies we should use in practice, depending on domains.
So you said EXP, sample from EXP. I'm not sure I
Oh, so
understand this part of the question.
if the goal is just to sample from exponential, like reward function, like let's say the goal is like standard goal in GFlowNet, and the domain is continuous, like image or like molecular conformation, which policies like do you recommend to use in practice?
I don't think there is like a generic answer to that. It really depends on the task at hand. But if your domain is unbounded, then I would say that the natural choice is to use a Gaussian, for which you need to learn the mean and variance. But if your domain is bounded, then you need to consider other distributions, such as the one I mentioned before, like beta or mixture of betas. But I suppose that, like I don't have an example on the top of my head right now, but there might be many other settings where the distribution you should consider is more tailored to the task at hand. And one last point is, I'll go back to this slide here where I mentioned that the choice of the family of distributions is really important, because if you make the wrong choice, then maybe your detailed balance or trajectory balance conditions can never be satisfied. So yeah, you need to be careful about the choice of distributions.
Thank you. For the molecular conformation, which policies did you use?
So this one, it followed let me go back to this slide. It followed this example here where there was a fixed number of steps. So it's called like stochastic control with GFlowNets, where we start with these abstract states and then we do 100 steps. And actually, I forgot which distribution we used. Maybe like Kolya, remember? I think it's Gaussian.
If I'm not mistaken, because it's a distribution for each dimension, you have a distribution over the circle. I think what was used is a mixture of von Mises distributions, or maybe circular Gaussians. Alex actually maybe can answer this better.
Yeah, I remember
in
that.
the room. Yeah, it was 10 steps in the paper and a mixture of 5 components, 5 von Mises distributions. But yeah, the details are in the paper.
Thank you very much.
Thank you for your question.
Are there any other questions? No? Okay, thank you very much, Salem. We'll resume in 15 minutes with the second hands-on code tutorial of the day. But before that, let's thank the speaker one more time.
Thank you.
So did you get that feedback?
Yeah.
Okay. Okay. Yeah, it's a good idea.
Let people cheat if they want to.
Yeah, no, that makes sense. I can do that thing. Especially because I have 15 minutes. push the solutions on.
Okay. Okay, we're ready to resume in just a couple of minutes.
Well, we're good to go.
Oh, in fact, we're good to go, but maybe the audience is not good to go yet. Right. So let me reintroduce Joseph, who will lead the second practical session of the day, in which you will train a simple continuous GFlowNet. Enjoy.
Thank you. Let's get online. So to facilitate this session, I've put the answers up for both the first problem set, but also the one that we're about to do. So you can have a look at the answers as you're working through it. Thank you. Although I'll continue to do the cooking show format. So the goal of this session is to do the simplest possible version of what Salem just described to us. It's almost cartoonishly simple. I don't think you'll ever actually use a continuous GFlowNet under these to do this sort of thing, but hopefully it allows you to understand a few of the core concepts. And at the end of this tutorial are links to a much more realistic and interesting continuous GFlowNet implementation in the GFlowNet library, which is being developed here at Mila, that I would encourage you to look at if you're interested in using these things. So the first step after you've got your notebook set up is to, as before, do your imports and run this hidden cell, which will then show you the hyperparameters that we'll be using for the beginning of our session. Okay, so as we talked about already, the big difference here is that we're going to be using our function approximator to predict the parameters of some distribution we're going to be sampling from, instead of predicting discrete actions. So this actually gives you a lot of power as a designer when you're trying to figure out exactly how you want to traverse your problem space for whatever set of solutions you're trying to sample. There's a lot of flexibility here. So, if you're predicting the parameters to say a Gaussian distribution, you can then sample values from that Gaussian and you can use it to modulate your current state in various ways, or you can just reset your current state to be those values. These are all design decisions that you have to make. In our case, we're going to be considering any value that we sample to be a delta of the current state. So we'll just simply be adding whatever we sample from our Gaussian to the current state. So S of t plus 1 will be equal to S of t plus this delta. A key thing here is that the distribution that we're sampling from can be a mixture of many distributions that Salem talked about. We won't be tackling that here due to just time constraints and the level of complexity that it adds. But I want to stress how important it is that this part be taken with care, because it's really a big it's a great way to introduce bugs into what you're building, and it introduces a lot of complexity. And the example that I point to at the end of this tutorial covers that very well. Okay, so what is our environment? What we are going to be doing is we're going to be sampling from a mixture of Gaussians. We're going to be learning to sample from a mixture of Gaussians. So our reward distribution will be defined by multiple Gaussians, each defined by a mu and sigma. And the other thing that we're going to need is an initial value, S0. So just below here, I'll show you, there's a rendering of the environment we're going to be traversing. So the game is we're going to be starting from S0 and then passing that state, the state being the current X position, to a function approximator, which is then going to predict the values of a Gaussian that we're going to sample from, and we're going to try and move around such that at the terminal state, we'll end up in that location proportional to the reward value that you see here. And so this function that this little class that I've defined here allows, sorry, my computer is a bit slow, allows us to define multiple environments of varying complexity given these values that we pass in. So we'll do this a few different times with different environments. So you should be able to just simply execute everything up to this point and view the rendering. And we can start talking about policies, actions, and states. And so, as we've said multiple times, we need a distribution from which to sample our steps. And we're going to parameterize this simply as Gaussians. So we're going to be predicting the mean and the standard deviation. We're also going to put some enforce that the standard deviation has to be between 0.1 and 1 for now to help with convergence. And so those are some of the hyperparameters that were given to you at the beginning of the notebook. But later on, you can play with these things and see how that changes the behavior of the model. So the first function that needs to be defined is something that's going to take our neural network and our current state and is going to predict the parameters of this Gaussian and return it as our policy distribution, which is being shown here. So our model, which will return a batch dimension and then two values, one for the mean and one for the sigma. And then we'll just simply extract those values, although here we are enforcing those constraints that I mentioned before about the minimum and maximum value of that of the sigma. Then we're going to pass that into a normal distribution and return this. So again, that I hope this is all clear. But our state actually includes something else. So the first element of our state is the X position. We have something else, which is a step counter. And this is kind of important, although I'm not sure how clear that is already. The idea here is that, in GFlowNets in general, we don't want cycles. We don't want cycles in our state space. But you can imagine in this formulation, it's very easy to produce one. You could, for example, sample an action that's just +1, and then another action that's -1, and you've ended up back in the same location that you started in. One way to avoid this is to simply increment a counter for every step you take, such that you never end up in the same place twice with respect to the state space. Here, and also in order to make our life easier, I think before Salam was talking about, sampling the exit probability in order to allow for earlier termination and these kinds of things. We're not going to deal with this complexity either. We're simply going to terminate when t = 5. We'll take a certain number of steps and exit. But there's definitely more sophisticated ways to handle this termination. And again, the example that I point to at the end gives a good demonstration of this. Okay, so here's our first actual exercise. So what we're going to be doing is we're going to be taking a step in this space. So we're going to have an action, which is sampled from our distribution, our Gaussian. And we're going to take our state X and produce the next step of that very simply by incrementing the action and adding the action and incrementing the step counter. The other thing that we're going to do here is we're going to initialize the state, which is to say that we're going to produce something that starts at x0 and at t = 0. So I'll leave you a moment to fill the cells in, or you can just copy them from the answers if you prefer. something I perhaps didn't make sufficiently clear is that the initial value is stored within the line environment at the beginning. So I have the answer up here. I hope that makes it clear the structure of what X represents. So this function will accept the model, the state and the action in order to increment. And this function will initialize our state, which will allow us to move on to more interesting things. So this next bit is going to be, I think, probably the main chunk of what you'll have to do. So we'll leave some time for it. But what we're doing is a simple training loop. We're going to use trajectory balance. Recall the loss from before. So in order to use this loss, we're going to need to instantiate a forward policy, a backward policy, and then, oh, I think I have a typo here, but a forward policy, backward policy, and then our estimate of log z. And I believe I've implemented this. Oh, I'm looking at the solutions, but I'm pretty sure I implemented this for you. So this is simply to say that we're going to take in our X position and our count, and we're going to output the estimate for mu and sigma, both a forward and backward model. Log z is going to be a scalar that we learn. And one interesting trick here is that we're going to learn the forward and backward models with a slower learning rate than log z. This is a common optimization trick when using trajectory balance. So that's what this function is going to do. It's going to run every single time you train a new model, which will initialize everything for you. Okay, so now I'm going to show you the training loop, which has some things you need to fill in. It's greatly simplified. Why? Because we're using fixed length trajectories. So we don't have the probabilistic exit actions. And what we're going to do is we're going to use our forward model to calculate a forward policy, sample an action from that policy, and then calculate the log probability of that action, which we're going to increment onto log PF. And we're going to store all of our states in a trajectory. And then what we're going to do is use that trajectory to calculate the backward policy, so that we know which actions took us all the way through. And we're going to evaluate the log probability of each observed action under this policy. The trajectory dimensions are batch dim, trajectory, step, and state. Those are the three dimensions. And we're going to calculate the probability of the backward trajectory and accumulate this into log PP to calculate the loss. The log reward is going to come from our environment definition that we've given to you above. And I think that's all you need to know. So down here, this model, again, this will only take a few minutes to train. And spoiler alert, there's at least one bug in this, and that's intentional. So if it trains and it looks like it's not quite right, that's fine. But go ahead and look through this. You need to handle the sampling of the forward actions, and also the backward and the loss computation. Don't be afraid to ask questions. How many people have successfully trained something, even if it doesn't look perfect? Did I give some more time for this? Who would like more time? Okay, no problem. For those who don't know, distribution objects have a log prob method that you can leverage, which is useful, quite useful. I'm going to give just a few more minutes, and then I'll show the answer to this piece, which is probably one of the largest parts of the demo, and then we can move on. Right, so in the interest of time, I'm going to walk you through the answer. What we're doing here is we're going to sample from the policy distribution we calculate using our forward model in X to produce an action. And then we're going to calculate the log probability of that action under that policy distribution and accumulate that on log PF. Here, what's happening is we're going to take a step using that action, and then we're going to add this information to our trajectory. And we're going to assign new X to X and continue the loop until we finish our trajectory. The next thing that we're going to do is the backward trajectory. So what we're doing here is we're going to get our policy distribution with our backward model, and we're going to pass in some already computed element from our trajectory. Our action is the difference between this point and the point that came before in the forward policy. And our log probability of that action is accumulated on the backward log PB. Finally, we just fill in the loss here, which is the trajectory balance loss we've already seen before. And that's it. Now, if you were to train this, it should take you about 1.5 minutes. You can run this function here, which does inference. So this just samples a bunch of trajectories and gives us, we get the terminal actions out of these the terminal states out of these trajectories, and then we can plot them using this handy render function, which will give you something that looks like this, which is bad. We haven't sampled the reward distribution. And the question is why? So hopefully if you haven't been able to fill in the code, you can just copy stuff over from the solutions notebook. I'm going to move ahead because I need to explain the bug that was present in the previous training loop. So what happened was during our forward sampling, we started at S0, which is predefined, and then we're sampling these, we're predicting the parameters of Gaussians and taking these steps from those Gaussians all the way to the end of our trajectory. In the backward trajectory, we did the exact same thing. But the problem is that at S1, we sampled an action to get to S0. S0 is a defined point. It's not something that we could sample and hope to get to with any level of consistency. And for this reason, the correct thing to do would be to treat that jump from S1 to S0 as a known entity with a probability of 1. And we didn't do that. And it's the fix turns out to be very easy, although it's hard to find, which is in the backward loop, the way that we index the range of this backward loop. It should end 1 earlier. The reason why is because of the way that zero indexing works in Python and the fact that we're calculating the transition between t and t minus 1. And the fact that a probability 1 event has a log probability of 0, so we don't need to bother accumulating anything. And so in this training loop, which has everything filled in for you, except for one fix, you can produce a much better sampler. So I'll give you a quick moment to run that and train it, and then you can look at the results from this. This is a very common bug. If what I said doesn't make sense, please feel free to ask questions. That's the beauty of these kinds of interactive tutorials. So if you change that number, you get this, which is pretty good. It's not perfect, but if we train for longer, it would be very close to perfect. We've now learned how to sample from this mixture of two Gaussians. So I'm going to make the problem harder by moving the Gaussians further away. We start in a very low probability region. We need to learn how to sample from these two Gaussians that are further away. So I've given you, you can reuse the previous function, just train it yourself and see what happens. And this, what happens very regularly is the model will learn how to sample from only one of them and will not bother learning that there's another mode out there to sample from. And we heard it earlier today about how to handle this sort of thing. We need off-policy exploration. And the first thing that we need to do basically is to define our off-policy method so that we can sample from this in order to produce the exploration required to find all of the modes. And since we're sampling from Gaussians, an easy solution would be to just increase the variance of the thing that we're sampling from in order to make sure that we're searching more on the left and the right of wherever we currently are in order to ensure that we find those other regions on the number line. So I'm going to assume that you're given a number of some kind, off-policy noise, and the goal of this cell is just to produce a second exploration distribution that incorporates this information in order for you to sample off-policy. I'll give you a moment to do this. Then the next major thing, which is integrating that into the training loop that includes off-policy exploration. So to give away the answer, all we're doing is we're taking the policy sigma, and we're going to add the noise to it in order to produce the exploration distribution. We're going to return that. Then the real question becomes how to integrate this into our training loop. So in the below training loop, let's fill in all the necessary pieces. We have to define the value that we're going to increase the variance by. This is what we're going to pass to that other function. Oops. We could also put this on a schedule. That would be ideal. So something that starts from some initial value and then decays towards 0 as we train. You can do that if you'd like. Then we're going to do sample actions from the exploration distribution, and then we're going to calculate log PF using the log probabilities of the samples from the policy distribution. And so you can fill in these pieces here in the training loop, and then verify that you're able to recover both modes in the environment. Has anyone been able to get it working? Sample from both modes? Yeah? Does anybody want more time? Yeah? A little bit? Okay. Oh, oops. Maybe that's me. No problem. In any case, in the interest of time, I'll draw your attention to the slides or the notebook on the screen, which explains what to do. So if you wanted to do a schedule, which I think is a good idea and might be necessary, I'm not sure if anybody's successfully trained a model without a schedule. A simple solution would be to start from some number and then linearly reduce towards 0 over iterations. So you can do that with just a simple linspace. And then as you iterate, you simply index the exploration schedule and you feed this into your function that you previously defined, which is going to give you a policy and exploration distribution. Those two things here and here, you use the exploration distribution to sample an action, and then you calculate the log probability of that action under your policy distribution. The rest of the loop remains the same. I don't believe there's anything else to do. And if you were to, this is training on my machine. If you were to do that, you should receive a plot that looks something like this. You have successfully recovered both of the modes. And okay, so for the final example, because we only have a few more minutes until we'll socialize. I'm just defining a sort of harder environment. Now I have 4 modes. Some of these modes have higher reward values than other ones. And we're going to simply train once more on this, but I'm going to give the model a fighting chance. So I'm going to give it twice as long to train. So go ahead and give this a shot and see what the results look like. And if you're having trouble getting things to work, of course, you can always use the solution notebooks to copy over anything that you need to find. Okay, so I mean, hopefully it's all running for everyone. It shouldn't work. If it did work, you did magic. But what we'll see here is that the model tends to prefer sampling from these higher reward regions and hasn't yet learned how to sample from this mixture of modes in the middle here. And this can be done if you train for longer. It could also be done if you were to find better hyperparameters, these kinds of things. This is the reason I'm showing you this is just to sort of highlight. I thought we had 3 minutes. Just to highlight how even seemingly simple examples can be hard to train, and how carefully you'll need to tune these your models if you want to use them to sample from these kinds of distributions. Really, the reason I'm showing this is because if you're going to use this in any sort of application that has a lot of dimensions and these kinds of things, I think things can get quite tricky quickly. And I would encourage you to sort of respect the challenge of applying this method in those kinds of domains. To give you, I think you'll have to do this at home, but to give you some intuition for how the different hyperparameters affect the convergence of this thing, I've given you at the bottom of this notebook a full implementation as a single cell, and you can play with all the different hyperparameters and see how that affects training. But the final thing I'd like to highlight before we end the session is a much more sort of realistically challenging example that I wasn't sure that I could do justice to within an hour, but I think is like a really good way to learn about the complexities and intricacies of using continuous GFlowNets. So this is the continuous cube environment, which is in a sense an n-dimensional generalization of what we've done today. From the GFlowNet library, which is written by multiple people that were involved in this workshop. You know, there's some instructions here on how to get things set up and training. But the link here, just to highlight, how do I make this go away? There we go. The link here to the continuous cube environment has excellent documentation, but it's also it's quite long. There's a lot of logic that's handled in order to make this sort of thing work that we were able to avoid because I oversimplified everything for you. So if you're really interested in understanding how continuous GFlowNets work, I would strongly recommend you go through this sort of extended tutorial, if you will, or example in detail. It handles the early termination. Oops. It handles early termination. The action space is governed by beta distributions with scale parameters. So that, you know, this is actually an interesting, this adds some interesting challenges when you're calculating the log probabilities. The forward and backward actions are governed by different distributions. That's another complexity that we avoided here, which is something that is actually very common when you're applying these things. Yes, I already mentioned the log probability thing. So I'm really only scratching the surface of continuous GFlowNets, but I hope that this helps ease you into some of these more realistic examples that you'll find online. Thanks for your attention. All right, now I need to announce things. There is going to be a social just over here, and there are drink tickets with the wonderful organizers, Mathieu and Emmanuel, who's, I'm not sure, I think she's over here at the door. So please grab some drink tickets and enjoy the rest of the evening.
Yeah.
Yeah.
Social event is until 8 p.m. So there's food, there's drink, and there's you to have fun. So please enjoy.